Hello, can you hear me?
Yes, sir.
Okay. Yeah, sorry, there's some technical problem. Okay, so we'll start now. I think already a lot of people have logged in, and others, it is also being live streamed on the YouTube. So in case someone wants to see on the YouTube. So what we'll do is in this basically 3 lectures today, this evening, on a Sunday evening. I'm very happy to see that students who are interested in physics, that they're spending their Sunday evening for this. What we will do in 3 parts, we will cover the basic concepts of physics. Right from, we will, to understand basic concepts of physics, we need to understand the atomic structure, radioactivity, what are electromagnetic radiation, and how X-rays are produced. And then finally, we'll come to the basic radiotherapy treatment planning and also radiation safety. So I'll talk for about 50 minutes, then we will have a break of maybe 15-20 minutes in which you all can just take a break or revise through some of it, then we'll go to the next part. So, what in radiotherapy, what we do and how this is done. And this is important to know how this is done, because just a general thing. What we do is give energetic, which is ionizing radiation to the tumor. And when we say give, that means it is absorbed. The absorbed radiation, it deposits lethal energy within the tumor cells, thereby killing it by damaging its DNA. That's the crux of it. But the radiation given to the tumor also traverses through the normal tissues and causes biological side effects, so which are not intended, which in this case is radiation damage to the healthy organs. And this radiation damage to the healthy organs can be reduced by reducing the radiation dose to the normal tissue to within its tolerance limits, through that by the knowledge of physics and the technological advancements, and through radiobiological principles by fractionating or dividing the radiation dose in whatever 5 fractions or 35 fractions, given once a day or more than once a day or once a week by the knowledge of radiobiology. By doing this, we give high enough ionizing radiation dose to the tumor, which by being absorbed with that tumor cells damages its DNA and kills the tumor. And while doing this, we see that the damage to the normal tissues through which the radiation beam traverses or exits is not damaged to that extent that it cannot recover or has side effects. So this is all the whole thing is about, to put in a very simple layman's term. So how it is produced, this radiation beam comes through LINACs, linear accelerators, and telecobalt, and they produce these high energy mega voltage radiation beam. The beams are shaped and they are directed on the tumor, and the intensity of the beam is modulated in a way to get the desired dose to the tumor while limiting dose to the normal tissues. Again, it's a very simple way of describing. And the spatial distribution of the absorbed radiation dose is based on the type of, on its type, energy, and interaction with matter before it enters the human body, because it comes through the machine. So there are things which come in between the radiation beam and the body, and after it enters the body. And for us to have a given absorbed dose within this region, the exposure dose of each beam is calculated, it is delivered, and it is monitored. That as to what we were someone's put in the chat box, no audio. Hello.
Sir, we are able to hear you, sir.
You're able to hear us, huh? So maybe some people have issue with their audio. Okay. Okay, thank you. So for a given absorbed dose, we want, okay, this tumor to absorb this much of dose. Gray is the unit of absorbed dose. We know that if this is the exposure dose from each beam, that we calculate that how much monitoring unit or centigrade we have to give, how it has to be delivered and monitored so that this intended thing is achieved. So ionizing radiation here, I'm referring to, it is emitted from a radioactive source or a target of an X-ray machine or a LINAC. That's where it comes from. These are the only two sources of ionizing radiation. It travels in straight lines in free space. And when traveling through any media, how much of the incident radiation is absorbed or scattered or weakened? When I say weakened, it means attenuated, or exits, will depend upon the type and energy of the radiation and the type and amount of matter it passes through before it enters the body and within the body. And after it exits the body, then we are not interested, except radiologists will talk about it. And a clinically useful radiation beam can be shaped the way we want it to be shaped, and of course of the desired size. I mean, it's not infinite sizes we can get. It can be given from a direction we want and focused to areas we want. This is all through technology. We are not discussing technology here. And it can be modulated in terms of its intensity the way we want. Either the entire beam, its intensity is modulated, or parts of that beam, the intensity is modulated by using wedges, tissue filters, tissue compensators, or by intensity modulated radiotherapy. And to get a prescribed radiation dose to be absorbed in the tumor-bearing area, which is what we call target volume, the size, shape, direction, and modulation of each beam is planned, and the calculated exposure dose is delivered and monitored. So this is basically clinical radiotherapy in a nutshell using ionizing radiation, and it's always with ionizing radiation. So in this sort of cartoon, what I've shown here is I've shown radon, radiation oncologist, and this is absorbed dose. So radiation, and this is I've showed radiologist and absorbed dose. So a radiation oncologist is only interested in absorbed dose. And why I say so? Because radiation oncologists are interested in the biological effect on the tumor. That is all we want to do, is cause a biological effect, kill the tumor cells. So we are interested only in the absorbed dose. Whereas radiologists are not at all interested in absorbed dose, because absorbed dose in diagnostic radiology, we are not doing X-rays or scans to have the dose absorbed. They want only the exit dose which come on the scans or on the X-rays, and that is not possible. So radiation oncologists, we say, when you think of a department, radiotherapy department, we give radiation, whereas in an X-ray department, radiologists take X-rays or scans. Take means they're interested in what comes out of the body, so that they collect the exit beam. Whereas we give radiotherapy, radiation, that means we're interested in the beam which is absorbed by the tumor. So this is a broad, how we differ. And how it matters is that the type of interaction of the X-rays, the type of beams we use, the energy of beams we use, type of beams we use, and how it interacts with the matter will decide how much of it is absorbed and how much of it is exited, and the way it has undergone changes before it exits the body. So in this, we had discussed earlier in the previous lecture that the Astro had a core curriculum course. They had formed a subcommittee which looked at the training of medical residents, radiation oncology residents in physics. And what they said, which is very important, is that, instead of learning physics over a period of few years, when you join a department, when you start doing some aspects of physics, it is very important for you to know. And that should be initiated at the beginning of the residency program. And if you have that while you are doing your clinical work and while you are involved in the treatment planning process, you will learn much more. What you see, what you understand, the basics, you will understand more. You will ask the right question. When you will read further, you will understand it better. So what I have sort of structured this talk, and I will talk about this, is to understand how ionizing radiation is produced. That also we have to understand. And interacts with matter, we need to understand. We need to understand what are molecules, atoms, not just atoms, but subatomic particles that make the tumor, the body, the X-ray target, and the radioactive material. Everything is made up of, atoms and subatomic particles. Then what are the universal forces? The gravitational force, the electromagnetic force, then strong and the weak nuclear forces. There are only 4 universal forces that we know as of now. The atomic model, and for most of the radiotherapy and radiology, the Bohr's model is sufficient. But of course, if you understand quantum physics, it is better. The periodic table, we're talking of the modern periodic table, and the chemistry and physics of different types of biological and non-biological material. For us, chemistry is not so important, but if you were in a nuclear medicine, then radiochemistry is very important. Then how the X-rays or gamma rays and the subatomic particles, which are electrons and protons, they interact with the matter in terms of photoelectric effect, Compton scattering, and pair production. The inelastic scattering, elastic scattering, and coherence, we are not talking about now. So these are the main things that we want to discuss. So the Bohr's atomic model and the quantum dynamic model of nucleus and orbital, that is very important, because when you will discuss about, we will discuss later about how X-rays are produced, the type of spectrum, continuous spectrum, blind spectrum, all this will be important when we talk about the filters that were used on the X-ray machines in the next lecture. Understanding the model is very important. The whole of radioactivity cannot understand unless until you understand the nucleus. Well, you may not, remember that even protons and neutrons are not the fundamental particles. Like proton is made up of 2 up quarks and 1 down quark. Neutrons are made up of 2 down quarks and 1 up quark. And of course, then there are force carriers. So just to suffice to say that there's nucleus, which is in the center, which is very tightly bound, protons and neutrons. Hydrogen atom is unique, that it has only 1 proton and no neutron, and then 1 electron. And then the moment you go to helium, helium would have 2 protons, and so which is the atomic number, and 2 neutrons. So both together give the atomic weight. And of course, as many protons, you will have as many electrons in the orbit in the beginning. And later we will talk about the NZ ratio. And henceforth, and I will talk about the different shells later, shells or orbit or orbitals, as we move from Bohr's model to the quantum dynamic models of the nuclear atomic structure. So, we don't need it all the time, but to understand what causes radioactivity, I think understanding these forces and even electromagnetic forces are basically there are four fundamental forces in this universe, which is gravitational force, which exists, it is universal everywhere, and it is infinite. The farthest body in the universe and us would also have a gravitational force, but of course it will be very weak as the distance increases. The electromagnetic force, which works between different particles of same charge or opposite charge in a different way. And here, of course, it is dependent on the distance. Then the strong and weak nuclear forces. The electromagnetic forces also have infinite range, but it is many times stronger than gravity. So electromagnetic force and the weak and strong forces are effective at a very short range, basically femtometers. They are in such a short range. And weak force, although it is called weak force, but it is still much stronger than the gravitational force. It is not less stronger than the gravitational force, but compared to the other three forces at that distance, it is the weakest of the three forces. And sometimes you don't realize that how these forces come about. It is so they result from exchange of force carrier particles. So when we talk about the nuclear physics and you go into the deeper layers of it, and they belong to a broader group called bosons. And the particle of matter transferred discrete particles of matter, they transfer discrete amounts of energy by exchanging bosons with each other. And each of these four fundamental forces has its own corresponding boson. So for the strong nuclear force, it is gluons, which sort of exchange between them. Then for electromagnetic force, it is carried by photons, when we talk about the photoelectric effect. Then the weak force is by W and the Z bosons, so weak nuclear forces. And for the gravity, so far we have not discovered it as yet, but it is predicted that for the gravity also there will be graviton, which will be the corresponding force particle of gravity. And you look at the CERN website, it is described in a very simple layman's term. So periodic table, where as students, it was a nightmare to study all the big, and this is a modern periodic table. The Mendeleev periodic table, it was very good. And before that also people had proposed, but in the modern periodic table, it takes care of a lot of deficiencies. It is now based on the atomic number. That is primarily an atomic number. If you look at how they are series, so there are periods and there are rows and groups. So the alkali metals, you see one, so these are valence electrons. So here a valence electron will be one, which is on the outermost shell. So the alkali metals, then you have the alkali earth metals, then these are transition metals in the yellow. Then these are the rare earths and radioactive. So these are the lanthanide and actinide series. So from you see this is from the atomic number of 57 to 71, they are grouped together in one here, and then from 89 to 103. So these are heavy metals. So these are rare earths and radioactive earth metals. And then on this side, on the right side, if you go, then you have in between, you see this green row, it is going diagonally. So this is the semi-metal. So if you look at most of the semiconductors, so their property like metals, they conduct electricity and heat and other things. Whereas semi-metals, so on this side, they will be conductors. On this side, carbon does not conduct. On the right side, so these are non-metals. And of course, on the right-hand side, these are noble gases. Hydrogen is treated separately because it has so many different unique things. It has just got one proton and one electron. So these are the like silicon. Silicon, you call Silicon Valley because semiconductors are there. And we won't get into the details of it. So these are in between metals and non-metals. So why we need to understand the periodic table? Because especially in terms of radioactivity and the shells, all that is decided by the how elements are structured. So how many electrons will be in an individual shell? So if you look at, so there's a principle of, so this is the principal quantum number 1, 2, 3, 4, and these are orbitals SP, D, F. The order in which these shells are filled is, this is the order. Then you say 1s, 2s, 2p, then 3s, then 3p. So why this is happening like this? It is the Aufbau, which is a German term for building up principle. So orbitals of low energy are filled in first with the electrons, and then only the orbitals of high energy are filled. And it's a diagonal rule in which orbitals with a lower n plus L value are filled before those with a higher. And it is, so this is the principal quantum number, and this is L is the azimuthal quantum number 1, 2, 3, so which corresponds to that. So this is how the shells are filled in the atoms. So more for in terms of radioactivity, if you look at, you have divided it into the blocks or families, SPDF, because look at the spectroscopic line, they are either sharp or they're principal, diffuse, or fundamental, so SPDF. And we have already discussed how on the Aufbau principle, the orbitals of lower energies are filled first, and then only the orbitals of high energy are filled. And I just won't go into the details, just to say that the radioactive materials are in the F block, which is rho -2. You look at so this is the lanthanide series, because the first element in this is lanthanide, and this is actinium, so actinide series, so lanthanum and actinide. So these, we will talk about radioactivity, we will talk about these. Now coming, so we have discussed the atomic structure and then the energy. So energy, in this world is, and when you talk of the electromagnetic radiation, so it depends on the wavelengths. The wavelengths is the distance between the peak of two waves. So wavelength here is very wide, as here it is very short. The wavelength is very narrow, and as the wavelength decreases, the energy of the beam increases. This in this chart it is shown as energy, which is very low to this is very high, and energy as measured in electron volts. So from radio waves, microwaves, infrared, visible light, what we see, then ultraviolet, which could have some biological effect, it could harm. The X-rays means low energy X-rays, and high energy X-rays or gamma rays, which are used. So as the energy increases, the okay. So this I showed in the previous one of the earlier slide on arts, and so humans have always, liked and praised to sun gods and goddesses. So in different cultures, civilizations, there has been a form of sun god. In India, it is Surya. Somewhere it was Apollo. Somewhere it was Ra, and so forth. So we as radiation oncologists, we are the modern peaceful energy worshippers. So I mean, it's not new. We use that energy, like humans have always used the energy from the sun for various things, good things. We have used the energy of the most intense energy, the intense form of energy, and the most potentially dangerous form of energy. We have figured out how to use it for peaceful purposes in terms of treating cancer. So in terms of electromagnetic radiation, there are a few fundamental aspects of electromagnetic radiation. One is the dual nature of it. That is very important. So there's a wave theory and there's a quantum theory, which is now the wave theory, something you can explain very well with that, like diffraction and interference, and the quantum theory, through which you explain the photoelectric effect, the Raman effect. All the electromagnetic radiation in this universe, in the free space, they travel in straight line. That's why when we are talking of something we have to accept, just think of geometry. A lot of things would be explained by that. And in free space, they travel with the velocity of light, which is 3 into 10 to the power 10 centimeters per second. And if you remember this, it is once in an exam, we asked a student that how long will it take for the photon or the X-ray to come from the X-ray target to the patient's surface, or the isocenter, which is 100 centimeters. So how can you calculate that? It's a very simple, it is a photon, or whether it's a light, or whether it's an X-ray, it travels with the same speed. And the amount of energy in the photon, it depends upon the wavelength. Okay, so the Planck's constant and the h mu. So they transfers energy. And when they pass through matter, their intensity is reduced by the process of attenuation, absorption, and scattering. This is something which we will discuss in much greater detail. So electromagnetic radiation, the very basic aspects of it is, just give me a minute. So they transport energy through empty space and through basically propagating electric and magnetic fields, and they vary with each other, and they're perpendicular to each other, and it goes up and it goes down. It exhibits a sinusoidal variation of electric and magnetic field, and the distance between the two peaks is your wavelength. And so Einstein, people talk about Einstein. When we talk of Einstein, he's one of the world's most celebrated and famous scientists. So to begin with, he had a lot of things which did not work for him. He failed in this class. His thesis was rejected. He did not get a job, as a scientist or a professor initially. And the first thing that he did, or which a major thing, was the photoelectric effect, what we are going to talk about. So Einstein's solution, the mystery of the photoelectric effect, that is what earned him the celebrity and the Nobel Prize. And this explained that light was composed of individual particles, what we call now photons. So what was known that light could, induce electrons. Electrons could be emitted by that. And whenever electrons are emitted, you could measure it by change in the electrical field. You can measure the current. But what was seen is just by increasing, no matter how much you increase the intensity of the light or the amount of the light, it will not induce emission of electrons. Only when the intent or the light was of beyond a threshold frequency, even if it was of a low intensity, it would result in that. Means that lights were in packets, in quanta, so that light is not just one thing, which is you just talk of, its intensity, that it has energy. And that is a fundamental property of different electromagnetic radiation. And so photoelectric effect, for us, we look at it in a different way. I will explain in terms of what is the clinical utility without getting into the fundamental physics of photoelectric. But needless to say, this is what gave him the, so people ask, why didn't Albert Einstein win the Nobel Prize for his work on special or general relativity? Was he at least nominated? I found it interesting in Quora, someone has asked. And of course, Einstein is most famous for his E is equal to mc squared, how he looks, his hair, and this famous E is equal to mc squared. So this has reached the imagination of the common man. It's written on t-shirts, written on mugs, etc., etc. So the Nobel Prize. So what, one of the person who has written, who's a theoretical physicist, and I liked his answer. He said, Nobel Prize in 21 was awarded to Einstein for his services to theoretical physics, and especially for his discovery of the law of photoelectric effect. And he says that his services to theoretical physics clearly, absolutely included relativity theory, but the photoelectric effect was much more clear-cut and inarguably correct at the time. The Nobel Committee is quite conservative and doesn't give out prizes for things that might turn out to be not quite right. So they talked around relativity while making it clear that it was part of the reason that Einstein was deserving of the prize. And he says, notice that it is not worded for his discovery of the law of photoelectric effect and other services to theoretical physics. Rather, it is worded that for his services to theoretical physics and especially for his discovery of the law of photoelectric effect. So, needless to say that photoelectric was very profound. So the quantum dynamics, quantum mechanics, quantum physics was, got a lot of this thing from that. Now coming to what we need as doctors and as medical physicists, the inverse square law. So people don't sometimes understand. So I've used this, I don't know from where I got this. It's showing a section of a sphere, three hemispheres if you look at it. So inverse square law. So radiation is emitted isotropically. Just imagine there's a point source. So from there, it is emitted all over, equally in equal intensity in all directions. And if d is the distance from the source, which is basically the radius, the d1 is basically the radius of this hemisphere or whatever you take as a sphere, and E is the energy. To begin, if the energy was E to begin with, and at distance d1, that means radius 1, and this sphere where you were measuring initially, this was the energy. But when the distance increases, doubles, that means the radius is 2, then we know how it will be distributed again in the surface of the sphere. And we know the formula of the surface of a sphere is 1 by 4 pi r square. We're not talking of volume, but surface we are talking about. And that is how it becomes inverse. So it becomes inversely proportional to the square of the distance. So this is very important principle. Not only in brachytherapy, of course, in brachytherapy it determines the dose, but even in teletherapy, when we will talk about later, that inverse square law follows. So some of the things that we need to know is one is the electron volt and electron charge. So AMU is basically one atomic mass unit is 1/12 of the mass of a neutral carbon atom, which is 12, basically 6 protons plus 6 neutrons, and electron volt, which is the kinetic energy acquired by one electron accelerated through a potential difference, which is a voltage of 1 volt, electron volt, and which equals to 1.6 in 10⁻⁻19 joules in terms of energy. And one charge of one electron is 1.602 into 10⁻⁻19 coulomb. So what is a spectrum? So we will talk about, this upper graph A shows that it's a continuous spectrum, and then lower down you see there's in between there's certainly one line, that several multiple vertical lines. So the height of the curve or the vertical lines tells us about the relative intensity of the radiation. And continuous spectrum, all the wavelengths are there in a continuous fashion, and but their intensities may vary. That's why it will depend where the peak is. And the wavelength here, suppose you are heating something, it will depend on the temperature and not on the material. Whereas line spectra, which are only few discrete lines, so that, I mean, in terms, if it is in the visible range, and it will be a few different colors, and many are missing. So this is broken or discontinuous. So continuous or discontinuous, or continuous and line spectrum. And the line spectra doesn't depend on the temperature, but on the type of material which is heated, because each material has its own chemical property, if you remember the atomic model, and that's why it would emit light of a particular spectrum. So this is how it is, the different electrons. So we've showed this is the binding energy of different shells. So K shell is the closest to the nucleus. And we are showing one is copper, which is relatively lower Z material, other is tungsten, which is very high Z, or the atomic number. So look at the energy, the binding energy of in copper, the binding energy of the K shell is 9 keV. This is kilo electron volt, whereas in tungsten, the binding energy is much higher. It is 69.5. And as you go up in the Mn shell, the binding energy is very little, and same. But so it shows that the binding energy depends upon which shell it is and what is the atomic number. Because in a larger high atomic number, then the nucleus will be bigger. It will have as many protons, and it will be there will be much stronger force. So this shows that if an electron moves from one orbit or falls into another orbit, how much of the energy would be released, and that energy is released in the form of photon. And I think this shows, so this is the show for the copper. So the difference between the binding energy between L shell or K shell and M shell, and that's the difference which is which comes out. Coming to radioactivity, so Marie Curie, we all know about, have heard of Madame Curie. So she discovered two new chemical elements, two radioactive, radium and polonium. So polonium was in radium because it radiated, polonium because she was from Poland. So in honor of her motherland, she called it polonium. And if you look at it, this is the and so this is a number of protons, the Z, and this is number of neutrons. So this is a NZ line. So this is if there were equal number of protons and neutrons. If you look at up to say between 14 to 20 atomic number, the number of neutrons and protons in the atom are more or less same. After that, there are more neutrons, and I mean there are various things. I will not discuss about that, because as the nucleus becomes bigger, there are more protons, and because protons are both positively charged, although there are strong nuclear forces and weak nuclear forces, I try to keep them together. If they are too close, if they're a little away, then these forces will not work, and nuclear forces, and they may just sort of fly apart. So that's why these more of neutrons are there. But as the nucleus becomes heavier and more protons and neutrons, you will see that it starts to decay. So here it is, this is stable nuclide, and if you look at on top, like uranium and all, which is a very high atomic number, it fission. If you look at these green dots, if you can appreciate it, these basically fission happen there. That means they're unstable. They just sort of break apart into two daughter nuclei. If there is excess of, on this side, this is excess of neutrons. So when there's excess of neutrons, what will happen? Excess of neutrons, and in this part there is excess. Sorry, in the upper part of it, this is excess of neutrons. In the lower part, excess of protons. Lower part of this straight line. And when there is excess of protons, what happens? There is a beta particle is emitted. And when there is excess of so if you can see these small red dots, these small red dots are the protons. So because the protons were excess, one proton is emitted, then once a proton is emitted. So, and here these, if you can see these small violet dots, these are neutrons, because neutrons were excess. So one neutron is emitted, and when it is very heavy, it is, you either release an alpha particle, which is basically two neutrons and two protons, and it reduces the weight. And of course, it is also having emission. And in all these processes, it is also emitting gamma rays in many forms of radioactive decays. So this is showing the radioactive radiation and some of the characteristics. So the alpha decay, which is ionized, and of course it causes direct ionization, which is the energy is quite high and very densely ionizing. We will talk about it later. Then beta particle, which is just basically electrons, and electrons could have different energy, and depending on the energy, slow moving electrons would have a higher ionization density. Then you have a positron, is nothing else but a positively charged electron. And then you have a photon. Photon causes indirect ionization. We will discuss about this ionization. And ionization density is ions per micron of water. And photons of different energy will cause different ionization. And it is indirect ionization by the electrons it produces. And the range of ionization will depend upon the energy. If you look at, just compare these two electrons, which is high energy electrons versus low energy electrons, 1 MeV versus 100 keV, the range is much more, and this is in terms of microns. So radioactive decay. So when we are happening a radioactive decay, we were talking about at what rate with which the radioactive decay happens. So there's a term known as transformation constant. So which is the chance or the likelihood, which is called basically a probability, that an atom will change into in a second, is usually called, this is what is transformation constant. So this, if you look at the transformation constant, and from this is derived the other term in radioactivity we talk about, is the half-life, T half. That means at time point 0, whatever was the activity, radioactivity, after that period of time, the activities become half of it. The same value is used for when we talk of half value layer, or so here it is the T half, which is the half-life. Okay, so if you look at n by n0, so which is basically it's the exponential of transformation constant into time, and for half-life that means it has become time is half or 0.05. And whenever it is 0.05, then this transformation constant into T half becomes 0.693. So the half-life is 0.693 into this transformation constant. So this is the half-life. And if you look at the half-life of various elements that we use, and I've written down iridium-92 because the two most for radiation oncologists, it is cobalt-60. Iodine we don't normally use so much. Cesium, again, it is used in intracavitary. So cobalt 60, cesium-137. Radium is for historical reasons, we have to know radium, and iridium-192. So as you see, the mass number is different, atomic number is different, and the half value. This is just to give you an idea. We will discuss in radioactivity chapter, a separate chapter. This is, I'm just giving you a broad outline. So radioactivity is induced by either neutron bombardment. So when we talk about, in a nuclear reactor, so like phosphorus 15, when it's bombarded with neutron, it becomes P32, which is radioactive, and of course emission of a gamma ray. Cobalt 59, when it's bombarded in a nuclear reactor with a neutron, it becomes cobalt 60 that we use, and of course gamma rays come, and this becomes radioactive. And when there's a proton bombardment, like sulfur, it becomes 34 as 17 chlorine. The chemical changes. Here the chemical is same. Here the chemical has changed. And uranium fission, we will talk about later about uranium fission. If you in uranium 92 with one bombarded with one neutron, it results in many things. It could be cesium 137, then medium, neutron, and energy which is released in different forms. So this is the nuclear reactor. If you look at it, of course, by looking at it, no one can make a nuclear reactor. So these are, if you look at the uranium rods, these are the uranium rods, and they are separated by a moderator, which is like graphite or heavy water. And so the fast neutrons, they collide with heavy water or the carbon, and they become slow down. And the whole assembly is sort of surrounded, this entire assembly is surrounded by a thick layer of moderator material, which basically acts like a reflector. So, and in turn surrounded by a thick layer of concrete, because we don't want things to go out. We shouldn't have like what happened in the Chernobyl. And these are control rods, which are of steel, which are containing boron and cadmium. So they are lowered into the pipe so as to capture whenever excessive neutrons are happening, they will be captured by this. And if suppose you can see this is Stringer irradiation drawer, because a lot of neutrons are going there. If you want to make cobalt 60, you can just put volt 59 and for making radioactive material. So this is the fate and path of in this. So there are various neutrons. They will say like this is neutron number 1, neutron number 2, 3, 4, 5, 6 different neutrons. So number 1 just basically escapes from the pile. It just goes, nothing happens to it. It could happen. It just goes here and there and then escapes. Number 2 wanders around inside, and then it enters another uranium rod where it produces fission, because for fission, as we just showed, that you need a neutron. And same thing, some of them could produce multiple fissions, and as you can see, number 4, and it comes out, then again by it reflected again, it produces fission, and so and so forth. So and sometimes the number of neutrons become too many, then that's where we require the control rods, which will sort of take up all the excess neutrons so that we don't have run away. So I'm using this picture, I just told it. Has anyone seen a coconut being broken into 2 equal halves? Some people are very good in breaking a coconut, but seldom. This is what happens most of the times. Sometimes you will actually break into 2 halves, but it is, if you weigh them, they will rarely be of equal size. And same is true when a uranium atom is split. So fission of uranium very rarely gives rise to 2 products of equal atomic number, that is equal half. So this would have been equal half if this is a number, so which is the lowest probability. So most of them would be of slightly larger or slightly smaller than the exact half of it. and very few of them would be very small fragments, as we were seeing in this. So this is the relative amount. So that's why the abundant, if you have a nuclear accident, you say, okay, cesium, tellurium, iodine, all these are in abundant. So this, again, I will not go into the details of it, just briefly I'll talk, because I have to cover the interaction of X-ray with matter, is the growth of radioactive phosphorus due to irradiation of normal phosphorus. So you would say that it will just keep going up and up, but because it is also because what material you are producing is a radioactive material, that means radioactive material will decay also. So you will not be able to, it will go up and up, and after some time, it will sort of become a stable state. So this is a maximum attainable state. Okay, so it will depend upon, if we are showing here the neutron flux. So it will depend upon the neutron flux and the material. Both the things will depend upon how much of radioactivity you will be able to get. So that the neutron flux, higher the neutron flux, more the radioactive material you will get, and the different type of material. So these are the two factors. I mean, we won't go into details of it now. I think now we will talk about the charged particles and ionizing radiation. So heavy charged particles, which are protons or heavy ions, and lightweight charged particles. Sometimes you forget that electrons are also charged particles, but they're very lightweight. And the Bragg speed, and difference between photons and X-rays, and how do we prescribe electrons and why, and how do we prescribe protons and why. So this, if you want to understand later on, you will be able to, when we talk about the clinical radiotherapy, this will be relevant. So this is the Bragg speed, just to suffice that as it travels within a distance, it towards the end, its speeds become less. If you remember earlier, we were showing that a slow moving electron is much more densely ionizing, and as it becomes slows down, a charged particle, towards the end of its path, it releases all its energy, and so there is a certain burst of ionization, and this is a Bragg speed. So when we will talk about the clinical use of protons, we will talk about this Bragg peak and how we have to flatten this Bragg speed. Now coming to the interaction of X-rays with matter. So on the right hand side, if you see, there's a picture of a X-ray. It's an X-ray. This lady had a fracture, and you can see the soft tissue. You can differentiate between the subcutaneous tissue and the muscle tissue. You can see a bone, the femur bone, and then within the femur bone, you can see the metal with these screws, because this was used for fixation. And why you can see this, it depends upon the type of the interaction, and I will talk about it later. In this picture on the right hand side, what you see is the cloud chamber photograph, and this is from the London School of Museum. This picture I've taken from the Meredith Massey, and so in this they show the straight line. What you see is you can see this dotted straight line. So this is the track of a beta particle, so which is a high energy beta particle, and the shorter tortuous rest of the things are the shorter tortuous tracks of the electrons, which have been set in motion by the gamma rays, because you can see there in the gamma rays. And as you see, there is towards the end of their all of them, towards the end of their path, there is more dense ionization. And this is with the alpha particle in this lower panel, the particles, which is the beryllium nucleus, and an alpha particle, which is by disintegration of a nitrogen nucleus by a neutron. So this is the ionization. You can see the track of ionization, whether it is densely ionizing or sparsely ionizing. Now, finally, what happens when a photon is passing through a matter? So either there are four things would happen. It is deflected from its original path and then proceed in a new direction, but with unchanged energy. So that seldom happens, that without change in energy. It is deflected and also loses some of its energy. So it is, deflection means it is scattered. It disappears altogether. When it disappears altogether, it means it is absorbed. And transmitted unchanged, that means it just goes through and through without either moving from its path or without being reduced in its intensity. So this formula, I mean, whenever formulas come, most of us are sometimes put off, but I will explain, what this formula means and why it is that this is for the photoelectric effect. That's why I told you the story of Einstein. Although he was looking photoelectric effect in a different way, but now subsequently we have found that what are the factors on which photoelectric effect depends. So this is attenuation. Attenuation means reduced in the intensity of the beam. Attenuation by the photoelectric effect. So this is directly proportional. So on top of you see, so this is for the photoelectric effect, directly proportional to the Z cube. That means cube of the atomic number. That means as you increase the atomic number, the photoelectric effect increases, by the cube. That means it's very strongly, very heavily dependent upon the atomic number. And it is also inversely proportional to the cube of the photon energy. So this is h mu. So there are two main things for photoelectric effect. It's very important to remember. This is very important both in diagnostic radiology as well as in clinical radiotherapy if you are using lower energy X-rays, that this effect will be much more pronounced when you have a material which has high Z. And in terms of human body, materials which have calcium like bones would have high Z. Or if there's some implant, metal implant, and it will be, inversely proportional to the cube of the primary photon energy. That's why at lower energy, this will be much more prominent. So when you have a combination of low photon energy, like say 60 kV X-rays or 50 kV X-rays, and you have a high Z material like bone or a metal implant, then this will be a very prominent phenomenon. In diagnostic radiology, we basically take advantage of photoelectric effect because it causes differential attenuation within the bone by use of say 40 kV, 60 kV, 70 kV X-rays, and less of X-rays come out of it because in diagnostic radiology we take X-rays, and as I said, radiologists are only interested in the exit beam after it has interacted differentially with different kind of body tissues to give that contrast. And so these are the two main things. It is directly proportional to cube of the atomic number, Z cube, and indirectly proportional to the cube of the energy. So I think this is most important, and all of you should remember this. Just capture this in your mind. Now the Compton scattering is little more difficult to understand, but this is of the most maximum importance for those who give radiation. Or when we say give radiation, that means we are interested in the absorbed dose. And I will talk about later why this Compton effect is more important in clinical radiotherapy as compared to photoelectric effect. So here the photon is interacting with a free electron and is scattered in a direction. So if you look at this, is scattered in the direction by angle of phi, and the recoil electron, because it has been hit by the photon, that moves from the direction, the angle of theta. So the incident photon will transfer always. Whenever it hits, it will transfer some energy. If it is otherwise, if it is not transferring any energy, then it's a different kind of, then it's a Rayleigh scattering or some other. It just goes and without transferring any energy. Here it hits and transfers the energy, and the transferred energy is higher when the angle through which this photon is scattered is higher, and maximum is when it just sort of maximum 180 degree. Just if those you have played snooker, billiards, you would see that the angle with which you hit the ball with your striker will depend which ball moves in which direction and with how much of energy. Okay. So, and the change in wavelength, basically wavelength is the energy, is dependent on, it's a different way of putting it, is dependent on the angle of scattering and not on the material, not the energy of the incident photon. But as the energy of the incident photon increases, the fraction of energy which goes to the recoil electron increases and the scatter decreases, because that scattered electron would have that much more energy, recoil electron. So these and all of these have importance when we talk about how energy is deposited and how a clinical beam of higher energy photon would behave as opposed to a radiation beam, X-ray beam of a much lower photon energy. This we show the primary photon different energies just from 12.4 keV to 12,400 keV. So this basically it becomes MeV. Okay, this is the MeV. So the wavelength keeps on decreasing from 1 Armstrong to 0.001 Armstrong. So this is a primary photon, and this will also give rise to scattered photon. And the scattered photon is also quite energetic, even for a high energy. And the recoil electron. So if you look at the recoil electron, which is the initial energy, how much the photon had, and the scattered photon, how much energy, the difference of that has all gone to the energy of the kinetic energy of the recoil electron. The recoil electron here is much more energetic, and it has almost 96% of the initial energy it has. So in sort of a nutshell, as we increase the energy of the primary photon, and by this primary photon, you said not just photon, because what was the incident photon? The energy which is transferred to the electron, recoil electron increases, and the scatter decreases. And we'll talk about the scatter because this is a scattered photon. Okay, decreases, and the change in energy of the photon increases. So high energy radiation is less likely to be scattered, and the intensity of scattered radiation is also less. Now, if you see it here, so if you put it all together, so total scatter attenuation, sometimes to understand these, curves and become a little difficult and sometimes daunting as to what it means, just look at two things are happening. So things are being scattered, things are being absorbed, and as a combination of that, it is attenuated. So if something is removed from the path or it is absorbed from the path, and if you measure it at particular distance, you will see less of that energy. So the total scatter attenuation is equal to absorption plus the scatter, and it, as we just mentioned, the scattered we showed in the previous chart, the scatter decreases as the photon energy increases. The total attenuation, again, we have said, is less at higher energy, and that depends upon when you talk about the percentage depth dose. In the next thing, it will show that how the percentage depth dose decreases. And the absorption by the recoil electron increases steadily as photon energy increases up to 1 to 2 MB. And again, it's not beyond that, because after that, the pair production comes into play and the Compton effect decreases. So, all this sound little, how this is happening, but if you just go back and see what was shown in these graphs, it will become amply clear as to why it is happening. Now, this shows, again, I'm using the simple, I like the message, they're very simplistic. If you go to modern textbooks, sometimes they go into much more detail just to bring out some very finer aspect. But I think we don't understand the broad concept, and I think that is much more important to understand the broad concept. So here what it shows, these are different energy photons. This is 10 keV, 1 MeV, so 10 keV, then 100 keV, then 1 MeV and 10 MeV. So you can see the energy. So what is happening is, if you look at if you look at the envelope, so this is the amount of the scattered, radiation. So with increasing energy, direction of scatter is more forward. So if you look at it, maximum of the scatter is in the forward direction and very little behind. Whereas in low energy, 10 keV, it is almost same on all sides. It is like an isotropic. Okay, so isotropic means in equal intensity in all directions. So low energy radiation scatters equally in all directions, which is isotropic. And as we increase the energy, it is more in forward direction. And also because we've showed earlier that scattered radiation energy is less for higher photons, so it is also smaller. So the area that is also less. So you have less of scatter with high energy photons, and it is more of forward direction. Okay, so for this you understand, this is very important to understand why you get skin. What is the importance of megavoltage radiation? So to all this. So megavoltage radiation as compared to kilovoltage will have less of photoelectric effect, more of Compton effect. It would have less of sort of backscatter. Skin dose would be less, bone dose will be less, and many other factors. We will talk about it I think one more slide graph I will show, and then we will cover this. Then this comes the pair production. In pair production, the photons disappear, giving rise to an electron and giving rise to an electron and a positron. Positron is basically just the antiparticle of electron, and the energy is equivalent to the mass of the pair. We know that Einstein's famous equation E is equal to mc square. So we know what is the mass of an electron, and the same is the mass of a positron, just the charges are different. So this becomes, so each of them, electron and positron, the energy equivalent is 0.51 MeV or 510 keV. So together it will be 1.02 MeV. That's why this is a threshold energy. Before that, it will not happen. And in nuclear medicine, when the electrons and positron combine together, because the positron emission tomography, they cannot live like that for long, and then they will emit two photons of equal energy and in opposite direction, because it's not just the conservation of energy, it is also the conservation of linear momentum. That's another concept. I will not talk about it here. So based on that, they go in absolutely opposite direction of same charge. So when it is detected together, we know this is a point specially located from where this these two photons have come across. Okay, so the pair production, which is directly proportional to the energy, and there's a threshold energy, and increases as the photon energy increases minus 1.02, because that's the threshold energy. So if you put all these things together, so of attenuation, so scattering is decreases as the energy or kV increases, and is mainly independent of Z. Okay, this is the Compton scattering. This is the photoelectric effect is indirectly proportional to the cube of the energy and directly proportional to the cube of the photon. Okay, of the energy and the Z or the material. Or this is how you can write it. So we've said the Z or the atomic number of the material and the energy of this thing. And pair production, it increases with increasing photon energy after the threshold energy of 1.02, which is basically E is equal to mc square of the mass of an electron and a positron. I'm talking positron, not proton. So the total attenuation will be basically a combination of all these three things. So if you show it in for different material, if you show, so on top of it is copper, and then this is water. Copper is not really relevant for us now, but when in older days, when we used to use X-ray machines and for therapy and design filters for that, then of course understanding what happens in a copper is very important. But this is just to show the Z. So the density of water is 1, but not the Z, because it's a combination mostly is H2O. So the Z is 7.4, the atomic number of the water molecule is Z. As you see, in the beginning, photoelectric effect is more always, and then later on it's the Compton effect, and then after 1.02 is the pair production which starts. Whereas in copper, because it is a higher Z, photoelectric effect dominates for a higher, so more than 100 kV till that time, photoelectric effect is dominating, and then the Compton effect is there, but photoelectric effect is still there. So it's not that it's a cutoff that one photoelectric effect, when it will stop, then the Compton effect will start. That it's a continuous process, but they will dominate at some point of time. Like in this range, if you look at it, is mostly Compton effect. So water is more relevant for us because this is what human body is made up of, water, except for some bones. So for a large range of it, it is a Compton effect which dominates. Okay, and pair production is there, but it is for a very small quantity. So this is what it is summed up. Photoelectric at in high energy at number material. I think I've already mentioned all this is in the box. So, okay. So this shows the fractional reduction in a thin layer as compared to a which is constant, the thickness in centimeter of thin layer. So there are two different materials. In one we have higher Z, material A, the atomic number is more, and material B, the atomic number is less, and this is the energy. So the energy, E1 is of course a greater energy, and E2 is higher energy. So how the attenuation will be changed? So it's a attenuation is given by the thickness of a material. This is how to explain. Is a constant fraction given by linear attenuation coefficient. So higher Z materials attenuates more. So attenuation also increases with increasing thickness of material, and high energy beam is less attenuated by a given thickness of that. So it is inversely proportional to the radiation energy, and the linear attenuation coefficient is the fractional reduction per unit thickness of the material, and in this it is determined by using a thin layer of material. If you use a thick layer of material, because each layer of material will cause successive attenuation, so the beam that will reach the next part of the material would be already of a different energy, and energy is an important component of attenuation, so it will vary. So this is to understand. So to sum up this, while all this is happening, basically at the end of it, through the ionization, it causes the damage to the DNA, and there are different kinds of DNA damage: double strand DNA damage, single strand DNA damage. It is either a direct effect of the particles or the photons, causes indirect effect by producing the electrons or hydrolysis of the water by ionization. The effect, this may or may not be required, and there are various other factors of molecular radiation sensitivity. And just when we talk about the biological effect, there are so many things which happen. Like this is, you look at hypoxia is there, and other factors are there. I'm not getting into details, just to give you a flavor that after we have understood all the factors that determine our what kind of beam will be produced, how it will interact with matter, and the bottom line is we want to know how it will cause the biological effect, and this is what it does. We will understand later, but before that we have to understand how to use the beam of radiation, and that I will explain later. I think this first lecture itself has gone for more than an hour. We'll give a break. I don't think we can concentrate so much. What I will do is, after this, maybe after a break of 15 minutes, instead of talking about how X-rays are produced and linear accelerators, which is not very difficult to understand, you can read. One of the talks which I gave, which I was surprised that some of the students, even after they've attended the talk, they had not got the gist of it, very important things. So after, I think, a break of 15 minutes, today we will have only 2 lectures. It will become, I think, too much, for you all to understand, go through a 3-hour session. The first talk itself, I thought I will finish in 45-50 minutes, but I had to go slow to explain things. I will now, after a break of 15 minutes, it is 6:10, 6:12. I think 6:25, will come back again, and I will talk about the properties of a clinical beam and how it is used, how simple 2D radiotherapy and basic 3D radiotherapy. I will cover. So for some of you, it will be repetitive, but please listen to it again. It will help you, because some things you may not have understood properly. And again, you will say, different things. You will say why a wedge is to be used or not to be used, or reverse wedge, or get confused between why a wedge is used and why a tissue compensator is used, etc., etc. Okay, so I will just okay. Anyone wants to say anything? Okay, so the same session you have to join. It's not any other link. I'll just basically So in 15 minutes, 6:12, or shall we meet at 6:30? Exactly. 6:30 we will meet, and then we'll have just one more talk, maybe for an hour. And the next one about production of X-rays, I divided into 3 things. Production, basically X-ray and LINAC and various dosimetric equipments, all those I will cover that maybe in some other day. It will become too much. Thank you. So join back in at 6:30. Yeah, Kishan has asked, will you share this presentation for revision purpose? Of course, I'll share this presentation, and this whole thing will be on YouTube also, but I will also share on the Telegram group. I will put the presentation also, the PPT. Actually, the previous ones, I don't think I've put all the PPTs, but I will put this one. YouTube link. Okay, I'll share my YouTube link. If anyone else has, so this is Professor Rajiv Sarin. Anyone else has just put that YouTube link here. I'm just doing two things. Many of you have subscribed to the YouTube, so just put the copy of the link. Okay, so the Telegram link also some people don't have. So all the students who are on the Telegram group on the YouTube, please one of you share it, put it on this chat box. We'll start into. Welcome back. I'll just share my screen. Okay. Wait a minute, I'll just. Okay, so we'll start now. So now we'll talk about radiotherapy, basic, simple 2D and simple 3D radiotherapy, and the concepts which many times you need for your understanding. And of course, in exams, you would see all those. You have faced exams or witnessed how exams are conducted. Almost every examiner will put in front of you a wedge, physical wedge, and ask you, what is this? And sometimes they tell you, okay, pick any of these things, and they would expect that you will pick up the wedge. If you won't pick it up voluntarily, it will be pushed in front of you, and you would be asked to explain it. So this is I've taken from the other lecture I had given on analogy from art, that this basically how this painting being created, Mona Lisa, is by a masterly use of ionizing radiation. We're talking of making a painting, but we talk of dose painting, masterly use of ionizing radiation to paint the colors and lines of the required doses and intensity on the canvas of tumor without spoiling the normal organs. And that is all inside the frail frame of a human body. Why I say frail frame, no matter how strong you are, high enough doses of radiation can damage any healthy organ. There's no completely radio-resistant organ. So it has to be done very carefully. And for you to use the ionizing radiation in a masterly fashion, you have to understand it and what are the basic principles of ionizing, using them. In the previous lecture, we did this earlier this evening, we discussed the different kind of interaction of X-rays with the matter. We discussed low energy X-rays, we discussed high energy X-rays, which is basically the energy. Then we also discussed the material, which is like water-like material, which is most of human body and tumors. We discussed about bones and high energy material. So the Compton effect, the photoelectric effect, you will not call them as such, but you will see how the energy dose distribution happens and how we modulate that energy. It's all through these interactions. I was talking of dose painting, that the previous painting you shared. So there's also dose painting, the art of radiation. When we create different isodoses, we basically we want to see that this much dose of radiation is to this organ and this thing. So this is basically, if you imagine yourself to be in a creative role, not just creative role in the painting is not just using a brush and contour the target volume and an organ at risk, but to create or design or fashion the shades of color that you want for different tissue. And for that, this basic understanding is very important. So this we just covered in the previous lecture. All of you were there. I think most of you were there. And we give radiation, the radiation dose is absorbed, causes lethal effects, and we give it through Linux and telecoboards, which get beams that can be shaped and directed. And we will talk about how to shape and direct that beam. Ionizing radiation, again, we have discussed that, and we have also discussed about what is absorption, what is scattering, and what is attenuation. The attenuation coefficient, the scatter coefficient, linear attenuation coefficient, all that we discussed, and different types of radiation. Today we will talk about the type of radiation which is mega voltage radiation that is used in clinical radiotherapy. And teletherapy planning has evolved from 1960s. I'm talking of only the mega voltage era. I'm not going to the kilovoltage era. It's just like 2D planning, basically on the surface, or skin marking is just basically 1D planning, and conventional simulator, then 3D conformal radiotherapy with CT-based planning. Like when I was a resident, we were doing both 2D as well as 3D conformal radiotherapy. Initially, conformal radiotherapy was mostly with making blocks or customized blocks with cerebral blocks, and gradually once the MLCs became more common in most of the machines, then of course the shaping conformality is through use of MLCs, and of course then in 90s IMRT came with inverse planning, and of course now in the era of IGRT, 4D planning and delivery, and of course many other sophisticated. So there are several aspects. One is the principles of patient positioning and immobilization, and they are actually principles. If you understand them, you will apply them cleverly. Then what are the tumor and normal tissue localization within the human body, both clinical as well as image-based. And clinical is also important. Sometimes The mucosal spread, which you can see or feel, you would not see on an imaging unless until you have done some special imaging like MRI or something else. So both. Then what is the beam energy that you will use? What is the beam placement? How you shape the beam, how you modulate the beam, and how you calculate the dose that you want to deliver. The beam shaping and modifying devices, I'm just listing some of them right now. We will discuss later. One is the shield. Shield means you try to block the radiation beam. You can never block it completely because attenuation is, you never get 100% attenuation with the photons. It will reduce the dose by half, by half, by half. If you remember the radioactivity which we showed, that the T half, there it was a half life, there it is a half value. Okay. So there it was a constant. Here also it's a constant. So you reduce by every HVL, you reduce by half. So if you use 5 HVL of shield, again, this is a question so many times has been asked, and let me just mention this. 1 HVL shield will reduce it by to 50%. 2 HVL shield will reduce it to by 50% of 50%, which becomes 25%. Third HVL will reduce to half of 25%, which is 12.5%. Then 6.25%, then 2.4. So it will just keep, but it will never become zero. So beyond reducing it to a certain value, there's no point. There's no need to use 50 HVLs. So just basically most of the shields are 5 half value layers. So it is reduced, and then obviously there is scatter and other things. So there's no point reducing it further. Then there are wedges. We will discuss the wedges later. Then tissue compensators. Again, we will talk about tissue compensators. We'll talk about the missing tissue. Breast cone, I won't discuss now. I think hardly any department uses a breast cone, and they are so heavy things. They're not even kept in the exams these days. I mean, we have probably just discarded them. Then the bolus and the bolus effect. Sometimes you're not using a bolus, but because you're using a mask, thermoplastic mask, or the skin sort of folds onto itself. So it's a self-bolus effect. And there are a few other things. I mean, there are small things that are not, that Penumbra trimmers and all, which are not normally used. So I'm not discussing them. So the dose, this you all should make an effort to understand and read more, because this is 1 hour lecture, so I won't go into details of everything, but please try and read more. So the dose at a point inside the body, or it could be a phantom from a beam in relation to the surface. It could be the surface here, or a reference point. The reference point could be at any specific point, or a Dmax. Basically, you are looking at the ratio of the. So the ratio at the surface or a reference point or a Dmax to a point inside the body. Like so this point inside the body could be X. This is where you want to know what will be the dose here, and then the dose at the reference point. And this big D is the. Okay. So this D is the distance from the source at this point. X is the point where you want to see, and M is the maximum dose within the body, which is at the D max, and this small d is the distance between this. So this could be it depends upon various things. So what is the dose inside? One is the attenuation, as we just mentioned. With attenuation, the intensity of the beam is decreased, and we mentioned what all the factors on which attenuation depends upon. In the previous lecture, we spent so much of time discussing that. It depends upon how much of it is absorbed, how much of it is scattered. And anything which is sort of moved away from that, the measuring, whether you're measuring the dose or it has been absorbed before that, it is not coming. And as compared to the original beam, it is attenuated. So the attenuation will depend upon the depth inside the body, how much of the body that the beam travels. Sorry, it's a spelling mistake. The depth inside the body that the beam has traveled, the density of the medium through which it has traveled, what is the photon energy, and then if you have used any material before it enters the body, which could be the wedges, it could be shielding material, it could be a tissue compensator, or even the tray that we use on which you put the shielding material or any other thing. So all that will attenuate the beam. Okay, that is one thing. Then the scatter of the beam this is just measuring attenuation, then the scatter of the beam. So that will depend upon what is the beam energy. As we mentioned, as the beam energy increases, the scatter decreases. We spent in the last lecture. and the direction of scatter also decreases. Then the field size. So I'm sure you all can guess that the larger the field, more is the scatter, smaller the field, less is the scatter. The depth inside the tissue, the deeper it is, more is the scatter, and what is the intervening material. And this D is the distance from the source, which is the inverse square law. What is D? The inverse square law, as we mentioned, it is not just for brachytherapy, it is also for the teletherapy. And percentage depth dose, that means the dose from the surface to at a particular depth. What is how much percent it is? Suppose percentage depth dose is 50, that means its intensity is only 50% of what it was at the reference point. So the percentage depth dose increases, that means you have less of attenuation. That means more of the beam goes there. It will increase with increasing energy, as we have we discussed. Increasing field size. Why it increases field size? Because with the larger field size, there will be more of scatter which will reach there. That's why it increases field size. But of course, the effect is not as prominent. The most important factor there is energy. So energy is the predominant factor, and after that, it's a field size. Then source to surface distance, SSD. Again, it is sometimes counterintuitive that when you increase the source to surface distance and you're taking it away, maybe the PDD will decrease. No, the intensity will decrease, but the percentage depth dose will not decrease, rather it will increase. And the reason it will increase is because of the inverse square law. It is, remember, this is basically a dose ratio. We are looking at the dose from, suppose this was a cobalt 60, okay, or a 80 SSD linear accelerator, say from Dmax or a surface which was at 100 to a 10 centimeter depth. You're looking at what is the difference in the dose between at 100 versus 110 centimeter. But whereas if it was at a much higher dose, then you're looking at 10 centimeter, but that ratio is much less. And because of the inverse square law, as the distance increases, the inverse square law sort of weakens. For the same same amount of, or the same magnitude of distance, the decrease in the dose because of inverse square law would be less. Okay, so that means so the decrease is there. That means the percentage depth dose is more. Then the field shape, again, sometimes it is counterintuitive. Why in a circular field you would have a higher percentage depth dose as compared to a long rectangular field? But if you think of it, scatter is one of the important components through which a field or dose reaches at any point of time, because even though you're talking of high energy, but high energy beam is also scattered. It is much less scattered at the mostly forward direction, but it is still scattered. So in a long rectangular field, the scatter which reaches to the center, the measuring point, is much less as compared to a circular field, where from each place in that field, it is equidistant. Then this concept of tissue maximum ratio. So when we're talking of the type of radiation technique like SSD, source surface distance, you're just creating a single field, or a parallel opposed field where the patient turns, or you just simply rotate the gantry by 180 degree in parallel opposed, and you bring the posterior field or the other lateral fields at the isocenter, you will be able to do that. So their percentage depth dose is very handy. Now, when you're doing isocentric technique, that means your field size, because the isocenter you have brought to the center of the target volume, and then you rotate the gantry and collimator. So the source to surface distance keeps on changing. The source to surface distance keeps on changing, and the percentage depth dose depend on the SSD. So you can't be having PDD tables for so many different source to surface distances. So there, this concept of tissue maximum ratio or the tissue wear ratio. So, I mean, tissue wear was when there was nothing there. Tissue maximum ratio or tissue phantom ratio is the more this thing. So here, if you look at, so this isocenter remains at the center point. So the SS, so this does not change. So the inverse square law is not used. So it takes into account everything else except the inverse square law, because you're always measuring at the 100 centimeter. In a linac, it's 100 centimeter, or on a cobalt, it's 80 centimeter from the source. So in this, you look at the dose at different depths. So this is what the concept of relative dose or the dose ratio, either in terms of percentage depth dose, which is used for treatments that are single field, mostly used in palliative, sometimes even curative setting, or a parallel opposed field, where it is possible to see the setup and both sides and able to achieve the SSD, which is 80 or 100 centimeter on the field without much uncertainty. Then you can use percentage depth dose. And for each machine, for different field size, for different energy, you will have the percentage depth dose charts. And you should know, and there could be correction factors like, the equivalent field square, you would do correction factors, and anything else which comes in the field, you will correct for that. And source to surface distance also, SSD, if it changes, then you have to correct for that. Tissue maximum ratio, as we said, when the isocentric technique, TMR or TPR, you have the values, and some department use it in a different way, you should know, and that is how the dose is calculated. So how much should be the incident dose, and then monitoring units, how they're set, calibrated, how much should be the monitoring unit. And the percentage depth dose, you decide the time, what is the activity of your telecobalt source, or this thing, you calculate the time or the monitoring unit. So this, we have shown that this is a percentage depth dose. Here, this is shown in water because water is most important for us. And so this green line is the telecobalt or cobalt 60. So cobalt 60, and this is a different, and then this is one is the 6 MB, the black dotted line, and the red continuous line is the 10 MB. So these are the three different lines. Let us look at only up to 10 MB. There's not much point looking beyond that. And of course, 15 MB is the one beyond that. And these are different depths. This is 5 centimeter. This one is 7.5. This one is 10 centimeter. And I've also drawn circles. This is I've got 15 centimeter. So looking at the dose that you get at, say, 5 centimeter depth on a telecobalt, you get close to 80%, not exactly 80%. It is little less than 80%. For a 6 MV beam, it is around 84, 85, little more than that. And for 10 MV beam, it is little higher. So the trend in general is, see, the surface dose is not 100%. For a cobalt, it peaks, the Dmax is at 0.5 centimeter. For 6 MV, it is around 1.5. And then as the energy goes, it sort of increases 1/4 of the energy. And then after that, there's a gradual attenuation. This is, you can see that because the percentage depth dose, it becomes less and less. What is important to note is that as you increase the energy from cobalt to 6 MV, you get a major advantage. Then from 6 MV to 10 MV, again, distinct advantage. After that, when you increase the energy, it is not so much more increase in the percentage depth dose. And this is what we're talking of, one particular field size. Let us say this would be for the 10 by 10 centimeter field size. Look at the 15 centimeter. At 15 centimeter, even for a cobalt, if suppose your lateral separation was 30 centimeter and you were treating at a mid plane with a parallel opposed field, you were treating, suppose a large abdomen, you have to treat anterior and posterior, and you only have a cobalt machine. Your linac is not working on the machine, you don't get a linac, and you have to prescribe at 15 centimeter depth in parallel opposed. In a cobalt field, you will look at it only at that point, only 40% of the incident dose is going. That means at Dmax, you have 60% higher dose. It is much more. It will be more than double the dose. Okay, and if you're treating on the same thing, if you're treating on 10 MV, then your mid-plane dose is close to close to 60%, and you'll be better off. But still, because the percentage depth dose even here is not enough, so you might think of using a 4-field box. So looking at this just percentage depth dose, you can imagine if I was treating with one field, like in a palliative setting, if you're treating a vertebra with only single field, I am prescribing at this depth, how much of my target volume would be covered. If I was using 2 fields and they were parallel opposed, what will be the distribution where I will get hotspot? I will show it later. So the divergence, again, this question, it is almost everyone gets it wrong. I don't know why. So I have put this diagram. So that photon divergence increases with So people would say it increases with, like you're talking about, percentage depth dose decreases with, people would say it decrease, or increases with. People will say with increases with, um, it's with the energy. Okay, that is accepted. Then when we talk about the SSD, how it correlates with percentage depth dose, people get confused because they have not understood the concept. Same way, the divergence of photon, how it increases with, invariably people say divergence will increase with increasing SSD. And I don't know why sort of that answer comes intuitively to people, but I just want to show that with the diagram I put it. So let us say this is the skin surface, this straight line, and this dotted line is where you are measuring at say 5 centimeter or 10 centimeter, somewhere in this. This is the source. So this source is, let us say, cobalt 60, or even cesium used to have say 60 centimeter or 40 centimeter SSD. Then this is at 60 centimeter, which is used to have a cobalt 60 junior, cobalt junior at 60 centimeter SSD. Then we have 80 centimeter SSD, cobalt 60, and then Linux, which is 100 centimeter SSD. So for the same point here, if you look at, as the SSD increases, it is less divergent. And it's just to imagine what is the source of, parallel rays. When you do a physics experiment, in the light experiment, we take a sun rays. So the light is coming from such a far distance that it has almost lost its divergence completely. It's not that it is non-divergent completely, but almost non-divergent. So as the SSD increases, the divergence decreases, and this has a bearing when we are talking about field matching. When you're using field junction to adjacent field you are using, then this divergence matter, because you have to either take care of it or at least be aware that this beam is diverging and that it may be diverging into a critical structure, and that critical structure may be getting contribution from both the beams, as we will talk now. So can you completely eliminate the divergence from a clinically useful beam? The answer is no, you can never. I'm talking of a clinically useful beam. We are not talking of a pencil beam or something else for some specific irradiation or experiment. So when is it of special concern? As we just mentioned, when we have two divergent beams, and suppose you have brachial plexus or a spinal cord, and you have one divergent beam and adjacent to it another divergent beam. Just imagine, like in brachial plexus, if you were treating supraclavicular fossa with the anterior field and the breast with two bitangentials, and these are orthogonal. They are not in the same, this thing. So what happens that their divergence of one beam will go into the divergence of another beam, and there will be area which will get overdosed. Same is with the spine. If the spine is in an adult or a large child, if the entire spine in the cranospinal cannot be covered in one field, you will use multiple fields, and I will talk about the matching of the field. So how to manage? So this is one simple way. There are of course other ways. So one is that you use a separation or a gap on the skin between adjacent fields, and if needed, move the junction or spread out cold and hot regions by what we call feathering. We just move it around. So this is SSD. So there are two fields, and let us assume that both of them have the same SSD. Sometimes it is not the same SSD, because imagine the spine. Spine has a curvature. It has lumbar lordosis, and then the thoracic spine. So you have set it up, and it is different. Okay. So this is L1 is the field length of the first field, or let us say lumbar spine. L2 is the field length of the dorsal spine, and you want that depth that they should intersect each other beyond the spinal cord. And this I am talking about the traditional conventional cranospinal field we used to use. Of course, now many people use VMAT or other methods in that we don't have to do field matching or tomotherapy. But if you were using on a LINAC conventional two posterior field, which are, there's a gap in between. So the depth is the D is where you want that they intersect beyond the spinal cord, because spinal cord is the most sensitive, because you don't want the spinal cord injury. If they were meeting on the skin surface, spinal cord may get dose from both the beams, and you get overdose, and you get a complication. So just imagine these are two triangles. So this is one triangle, and this is another triangle. So you know the property of a triangle. So the separation, what you want to come, separation is S1 and S2, this together. How much should be the gap between the two fields on the skin surface? So which is half of L1, that means this, you are looking at this, half of L1, okay, and which is half of L1 D by SSD1, okay. So D is this depth and SSD1 plus, so this is, and this is plus 0.5, again half of it, because it is half of it, L2, this means this distance, this into D, depth is the same, by SSD2. So basically this is same as this. Okay, so we know the length of the field, which is this half of L2, we know the SSD, and here we know the depth D, we have to calculate the S2. So the S2 is the only unknown variable, unknown thing that you want to calculate, and S1 is the only unknown thing which you want to calculate. And because we know the three other things, we can easily calculate. The other way of taking care of divergence is with half beam block using asymmetric jaws. Earlier we used to use physical blocks, or for breast there was a breast cone with a half beam block to prevent the divergence. They were heavy, breast cones, and they were not only helping in field direction, but beam direction, but also beam blocking the divergence. So most departments now use asymmetric jaws. So you should know, when you're using asymmetric jaw, many times it is for half beam block. Sometimes you use it for other purposes, but so when you're using half beam block, then that is a non-divergent beam. Then mono-isocentric technique plus asymmetric jaw on both sides. So you know X and Y will change. The other thing which most departments don't do it now, and people can't imagine unless until they see it, is to, so just imagine if there is a supraclavicular field and a tangential field for the breast. So the tangential field of the breast is from medial and lateral tangent. It is sort of diverging into the neck towards the supraclavicular field. So to make the superior border non-divergent, you may move the couch by 5 degrees or 6 degrees, so the superior border becomes non-divergent or straight. But it will, of course, the divergence in the inferior border will increase, so that you have to take care of. And similarly, in between the cranial and the spinal fields, so when we talk about that, so we move the couch angle and we do the collimation of the cranial fields for CSI. And of course, when we increase the SSD, then there's less divergence. So Penumbra, again, I'm telling it because sometimes people do not understand this concept. I really do not know why. So I have drawn very big, bulky sources. Of course, you don't have such big, fat sources. So this is, imagine this is a source of a cobalt. It's a small source in millimeters, and a source of a telecobalt, which is in centimeter, 1.5 centimeter, sometimes say 2 centimeter also. So let us say 1.5 versus few millimeters. So there are two types of, one is the transmission penumbra. If suppose through the jaws or the MLC, depending whatever defines the beam. So if they are not shaped in a way that they move like an arc, and the shape of that takes care of the divergence of the beam, some of the beam has gone through full thickness of this, and whereas some of the beam has gone only through partial thickness of this jaw. And so as a result, there will be a dose gradient. So this is a transmission penumbra, and the geometrical penumbra is like, just imagine a thick source, a big fat source of like a size of a finger, or a telecobalt source. So this blue line is coming, it is coming here, and from the other side is the red line. So this, you get a large penumbra as compared to in a thin source. If you look at a small source, there also you have a geometric penumbra, but it's a very small geometric penumbra. So in general, you will find that when we say sharp beam, so Linac beam has short, a small penumbra, and of course because of higher energy, it has less of the scatter also. Okay, so and I'm just showing this picture that you want to create a fancy dose whether you for the protons or photons, and you need immobilization. So this just doesn't happen just like that. Whether it is with photon, whether it with proton, it requires a lot of careful treatment planning. And I will just tell you what are the simple aspects to understand the treatment planning process. Here, of course, it's the patient positioning and immobilization. Okay. Then this is just to show that what all contouring you do, you contour different, basically image-based planning is there. I mean, it is all image-based planning now. You contour different organs, the tumor, gross tumor, your JTV, the area where the tumor may be there, what we call the CTV. Then you give margins for the movement and setup errors, what we call, the PTV, and of course the normal organs you delineate and give margins. Now, this is just in a nutshell I will cover. So once you have decided that you want to give external beam radiotherapy, so you have to decide whether it's a palliative or curative radiotherapy, because intent matters. And again, but palliative radiotherapy need not be just a low tech, low dose radiotherapy. Sometimes you have to use a high dose or medium dose. And if you're using a high or a medium dose radiotherapy, even in palliative setting, and the patient is expected to live, say, a year or more, and then you have to think of using a better treatment planning process so that the dose to the normal tissue is reduced. Then you also have to look at what are the competing cancer or health problems with the patient, the logistics, how many times they can travel. So you may have to use hyperfractionation. And because you're using hyperfractionation to reduce patient's travel, and you're using high dose per fraction, and the patient happens to think patient will live for a year or longer, you may have to use more stringent planning. And then, of course, what are the expected acute and subacute toxicity, and whether you expect the patient to have late toxicity. And in a curative radiotherapy, not only this, when you're looking whether the child, growing child, what happens, if an adult, how fit or unfit that person is, how they'll be cooperative, what kind of dose fractionation you want to use, and the organ and body reserve. Someone has already pre-existing lung disease or heart disease. Taking into account all this, you decide whether you will do a simple 3D planning or a 2D planning, or a more advanced form of conformal radiotherapy planning, which may or may not require non-coplanar fields, or IMRT with or without image guidance, or special techniques like 4D MRT with breath hold or other respiratory gating or cardiac gating. Whether you use MRI also for the simulation, or just simple CT based planning. So I won't go into detail. I think I've just mentioned that the technique and planning complexity is based on all these factors. The bottom line is, if you read it, the planning time, treatment time, planning time is different from treatment time on the machine. The human resources and money that could be justified for that radiotherapy course in that patient with the above consideration. So taking everything into account, you decide how easy or difficult planning you want to do, how it will be delivered, how easy or difficult it is to be delivered, and whether it is really justified for that particular patient in that given clinical context. So just to summarize, simple 2D, again, sometimes when you're asked, okay, what should be there, you've taken decision making. I think these are the main concerns. Simple 2D planning or a 3D planning, if you have the facilities for complex 3D planning MRT. Some departments don't have, so don't have a choice. Every patient, either they treat with 2D or a simple 3D planning, or they refer outside if the patient can go. So mostly in palliative treatment, also in some curative treatment, if complex treatment is not useful and increases the integral dose, sometimes more complex treatment complexity you bring, it increases uncertainty and also the integral dose. In 2D and 3D planning, you keep positioning and immobilization simple. Most of the time you are able to see that. Planning is done with a wider margins on either a CT simulation, or if you're in your department, you have an X-ray simulator, it's very useful. Then diagnostic CT and radiological anatomy could also be used if you don't have an X-ray simulator, or it is not possible to do it for that patient. And of course, surface anatomy and skin marks. In our department, we were discussing why many residents these days really struggle to understand basic concepts of 3D planning or 2D planning, is because they only do CT based planning. They have not done X-ray based simulator planning. So some things, when you're doing X-ray based simulator planning, some things while you're doing that automatically you understand. Otherwise, you just patient have a CT, you say, okay, from this patient positioning, you do a CT from here to here, and then you contour MCT, and then some plans are made without you having understood. So any one of you, if you have an X-ray simulator in your department, at least for practice, do some planning on the simulator. You will understand the concept much better. Then of course, 2D planning, you could deliver either on a telecobalt with a shielding tray or any LINAC with or without, MLC. Even without MLC, you can do that. And treatment verification here in 2D and 3D planning is because finally what you are planning to do, you should know. It's not that 2D or 3D planning, you don't need treatment verification, only you need, complex 3D or CRT or IMRT. But this, you either, where the fields would be looking on the skin or the portal marking on the skin, or with or without imaging. You may correlate with bony anatomy. Like traditionally CS cervix or many head neck cancers, we were doing 2D or 3D CRT. We correlated with the bony anatomy and it matched perfectly, and all the long-term results are with that. And of course, in a complex 3D CRT IMRT, you have to have a reliable and reproducible positioning and immobilization, and that cannot be done without CT-based planning, without 4D CT. And many a times you would require MRI if the delineation of the tumor or the normal tissue is not proper, or not reproducible or accurate on CT, or sometimes use PET CT. And treatment for this, you will require a LINAC with MLC. In these days, you can't treat without MLC, without gating or other features. Okay, and imaging is necessary for verification. So this is, I won't go into details, but it is very important that people should know the patient, the machine, and the department. And patient, obviously, you need to know, but the machine is each machine. Many departments would have only one machine or two machines and the same beam matched. That will be ideal. If you have two machines, they are beam matched. I mean, that's a luxury only few people have. Some departments would have only one machine or three machines or five machines, and they are different makes at different time points, different versions. So each machine, you should know what are the different types of energies. It is only photons or photons plus electrons. What energies, what is the maximum and minimum field size? In some machine, you can only treat up to 35 centimeter field size, some machine up to 40 centimeter. Then what is the extended SSD and TSD, which it is possible and your physics department allows you to do. The machine type, what kind of jaws it has, what defines the field, MLC, the type of MLC, the shielding tray, what is the distance from the isocenter of the shielding tray, distance from the patient surface or the isocenter, what is the type of couch, what is its tolerance, mechanical accuracy, what is current mechanical accuracy in the recent QA. So all these are very important for you to know. And if you do not know about this in your department, and you don't have to remember for hundreds of machines, basically 2, 3, 4, or 5 machines you have to know. Some departments would have too many machines, but more or less, you have to remember. And of course, in this machine, for this kind of photons or this energy, what is the penumbra I am expected to get? What is the divergence? I think once you know that, and you already know what is the percentage depth dose and the TMR and all these ratios for different energies, that is all you need to know to imagine what will happen. Then each department would have some are common practices. They are ICRU and other organizations they specify, but some of departments have unique practices, both for machine QA, calibration, and dosimetry. So you should be aware of it. You should know what are the techniques that are commonly used and specifically techniques that have never been used. You may read or see something and you may design a treatment plan which has not been used, and there are higher chances that they will go wrong. Either it will not be possible to implement, or during implementation something would go wrong. Then each of the immobilization device, what is the random and systematic setup error in general, and in the type of patient that you have, what is expected. So I think I will not go into the details of patient positioning and immobilization, but you all should know that there is interfraction movement, there is intrafraction movement, and there internal organ. Whenever I talk of multi-fraction radiotherapy, this is important. And you have to decide how much margins you have taken, whether it's a palliative or curative, and whether they have taken this into account. I mean, it should not happen that you have not thought about the interfraction, intrafraction movement, and the internal organ. Position has to be as comfortable as possible. And why I say as comfortable? Because the patient is less likely to move, which is supine, neck neutral, arms by the side, heels together, toes apart. And this neutral position, comfortable, should be changed only if it significantly helps planning delivery of it. If you like, if the neck or the head, you have to hyperflex or flex it more, sometimes just to keep away the eye when you're treating a pituitary or something else, or a supracellular region, sometimes it helps. So, or to keep the spine straight or different. So, you or move your arms away from the field of tangential fields that will come in the breast. So, or remove the skin folds. So all these areas like head, neck, arms, knees should be, ankles should be well supported. Patient should not be in pain or physical or psychological distress. And you should know the departmental data about setup error, as I have mentioned, and what is applicable for this patient. So now the type of fields that we use, shielding and wedges. I think this is the really crux now where it comes, and then we will use the examples. So single photon field, all of you would have treated some patient with single photon field, but not commonly. You've seen mostly used in palliative treatment, like we're treating some spine or a rib or a sternum, but also some radical treatments or adjuvant treatment, as we would discuss later. Suppose you don't want to treat much greater depth. Electrons are almost always on face, single thing, but I'm talking of photon. Supraclavicular foci, you might very often you treat with single photon field. Sometimes, of course, they are also used if you are using IMRT, or even with the 3D CRT, sometimes a posterior field is used, but generally single anterior field, and many other examples. Then you have to see that patient position is optimal for the beam entry and exit and organs in between. So I think this is something which which happens in the department already. When you join the department, is not okay, this thing will be treated in this position, and you have not really given it a thought why this particular position is preferred. And there would be very important reasons. So they have, of course, through trial and error, but also there's a lot of logic behind why a patient is positioned in a particular way for a particular type of beam arrangement for a particular cancer site. So I think all of you, I cannot cover everything you have to see, and invariably that is the optimal position. Sometimes we can't get the optimal position because now we have to do a CT scan. So the patient with the immobilization device has to go into the bore of the CT scan. So we have sort of tinkered with what used to be the optimal position, but you should be aware of it. Then, as we discussed in the previous lecture, you should know what is the attenuation, absorption, and scatter of different energy photon beams in different body tissues, which is soft tissue, lung, air cavities, and dense bone. So these are the 4 types of tissues that we will do, and we spent a lot of time. But you have to be aware. That was the purpose of the previous lecture. When you're doing the planning and when you're thinking of what will be the dose, you know how the beam is scattered or absorbed and finally attenuated. Then skin toxicity. Be acutely aware of all the factors that determine skin dose and the toxicity. And skin toxicity is directly dependent upon the total equivalent dose and the fractionation. That means the rate at which the dose is being given. There was Strandquist plot. We will discuss skin cancers. We will talk about it. It's very well known, and also the field size. And why I'm saying that, be acutely aware, because you may have done a perfect plan. Everything is perfect. You're very happy and you are a physicist. You sort of, pat yourself back. But the whole world and the patient only sees the skin reaction. Okay. And some other acute toxicity. And if you have given a bad skin reaction, then that be considered by everyone else as bad radiotherapy and bad radiation oncologist, And one of the factors is there's a skin fold. So that's why in the planning positioning, in the patient positioning, you be acutely aware that there's no skin fold, and sometimes despite your best effort, skin fold cannot be removed. In that case, you have to see that you take it like an organ at risk and reduce the dose to the skin fold, or at least the base of the skin fold. And use the optimal energy. And the optimal energy is not always the highest energy. If you remember the percentage depth dose chart I was showing, that when you move beyond 6 MV to 10 MV, the percentage depth dose increased slightly, but the exit dose increased. And from 6 MV, if you go to 15 MV, your percentage depth dose did increase, but the exit dose, or the dose at 15 centimeter, also increased very considerably. So it becomes law of diminishing return. So therefore, a different body size for a different location, there's an optimal energy. Beyond that, it doesn't really. And you also should know what are the specific cases where the least amount of penumbra and divergence is very useful. Once you know that, you can decide, okay, what are the special things that you could use. And I'm talking of 2D and simple 3D planning to reduce divergence. Whether in this patient you have to remove the couch, or in this patient you have to give a collimator angle, or you have to use a gap correction. That is very important. And this patient, because of the penumbra, you have, instead of cobalt 60, you have to use a 6 MB beam because of the geometrical penumbra is much less on a linear axis. Suppose you're treating one eye, and the contralateral eye, the opposite eye gets much higher dose because of the divergence and as well as the penumbra. You could use the linear accelerator. Then the entry and exit of each beam, and that decides the direction within the body. That again, mostly it is set standard, and you have not really put a thought as to why in this particular location, in the 3D CRT, why we choose have a combination of left anterior oblique and right, and left AO, left anterior oblique and right anterior oblique, or 4-field box, or a 4, field, but it is not like a box, it's like a diamond shape, left anterior oblique, right anterior oblique, left posterior oblique, right posterior oblique, or it is an anterolateral field, or it is bitangential field. So there are many reasons, and it is not just the physics of how good is the position, it is what lies in the path of the beam. So for each side, whenever you see put a field, or someone has put a field, you think that why this has been the direction of this beam, why not the other way around? And in some cases it will be so obvious, you won't have, but you have to think. Many times it will not be very obvious to you in a 3D CRT plan or a 2D plan why this is a particular field direction or orientation. Direction could also be orientation, which in terms of we call it gantry angles. Why a particular gantry angle is chosen, and why in some of the fields particular collimation is also required. So this is what is very important whenever you do the planning. You try and understand. I'm sort of laboring on this point because once you understand, many things will become clear. And even when you do IMRT, IMRT is not magic. Okay, IMRT is not magic. Only when you started doing protons and all, then you don't have to think about this. But if you're using photons, this aspect is very important. Why you put your blocks, where you don't want the dose to spill, where the dose would spill, it all depends on this. Finally, use the logic of physics and knowing the anatomy to decide what is the beam arrangement. It could be parallel opposed, it could be single field, I've already said, whether it is parallel opposed, anterolateral, posterolateral, obliques, 3 fields, 4 fields. And once that you have decided, then comes how you would shape the beams, if some normal tissue is coming, and modulate their intensity if it is clinically relevant. If it is not required, you don't do that. So each of these steps are very important, and sometimes when we are doing the planning, we have not really paid enough attention to this. We just we do the contouring, someone does the planning and we say this plan looks very good, we have got good coverage, the volume, 95% of the volume is covered by whatever, 98% dose or 95% dose, lung dose, kidney dose, heart dose, spinal cord dose is very little. You become very happy. But you haven't understood how that particular beam arrangement, how that particular beam shaping, how that everything else has evolved over the last several decades. Okay, it has not just happened by accident. So when you are doing the prescription, so you should know that what type of machine you have, whether you have done X-ray simulation, and based on the technique, field placement being in it, you are likely to use. Decide the technique, field placement, and arrangement that you're likely to use, as we mentioned. You decide what is the patient position and immobilization suitable for the techniques to be used. So it is not just the patient, but for different techniques, sometimes different, sometimes you want more rigid immobilization. Decide how you do the planning, either X-ray simulator or planning CT, and use contrast only if it is necessary. Otherwise, you don't use contrast. Then fiducial markers which are visible and on less mobile region of skin, you do the contouring and the plan. Okay, so now this is just, so decide the margins around the PTV, which will depend upon the penumbra. So this is the PTV, and beyond the PTV, what will be your field margin? Decide the borders, different borders, superior, inferior, anterior, posterior, medial, and lateral border, which will decide your field size. Okay. Number of fields that you will use, a field arrangement, which is gantry angle, whether it will be SSD technique or SAD technique. And SAD technique, which is 80 or 100 as isocentric, which is kept at the center of the clinical target volume. Collimation of the fields is sometimes required if it reduces the amount of the organs at risk in the field and does not underdose or overdose a region of intersection with other fields. And if you're using parallel opposed field, generally the collimation that will be same in both the field. Otherwise, in one of the parallel opposed field is collimated this way, the otherwise is not, then you would have an area part of the target volume which is not covered in, say, right lateral field or anterior field and covered in the other field. Okay. Then couch angle, if is required, if you are using half beam block is not possible with asymmetric jaws or then you may have to use few degrees of couch angle corresponding to the divergence of the matching either cranial field or the other field, which is the this thing in the breast cancer. Shape the fields either with simple shielding material, custom or customized shields, or with MLCs. Of course, that is the most method. If you don't have MLCs, again, simple 3D CRT could be done with corner blocks or customize this thing, asymmetric jaws. And then for matching fields that we have already discussed, matching field, then selectively use non-coplanar fields and non-coplanar fields which are feasible. Many non-coplanar fields you will not be able to implement because when you rotate the couch by 90 degree, then certain the gantry will not either hit the couch or it will not be possible. So the field shaping to shield normal tissues. So one is the standard divergent or non-divergent block of 5 HVL, and now they are limited use as corner blocks and mostly in APPA and sometimes lateral field, because to place them it is not in a lateral field. You have to fix them, and sometimes they might move, so it should be reproducible. So just like say pelvis, you can shield the 4 corners. Then they are either rectangular or square. Sometimes they are triangular, and it could also be like pencil blocks. Sometimes they used to use in shielding the eye. Custom block, when it is more irregular shape, they are made of cerebent, which you can design, and of course multi-leaf collimator if it is possible on the machine that the patient is being treated. And how fine the shielding would be depend on the width of the leaf. Asymmetric jaws, collimation, all these things. Very important that you maintain adequate distance between shield and not the PTV, the surface of the patient, because otherwise the skin surface dose will increase. Also remember that beyond a certain depth, the shielding effect because of the scatter becomes less effective. So beyond a certain. So skin sparing effect, as I mentioned, people sometimes judge you because you have given a skin reaction. So they will say, oh, this department or this doctor or this machine is not good, or this technology because they got bad skin reaction, is because one is surface bolus. If you have used, or it could be immobilization device which could act like surface bolus, especially if it is not perforated, it is a unperforated or a distinct sheet. Skin fold self bolus I have mentioned. Then decreasing energy or Dmax decreases, because you remember in the previous lecture we just talked about the scatter reduces and its direction is also more in forward as energy increases. It's because the range of electron is less. So if you're using low energy X-rays, then there is the Dmax is less and you have high skin dose. Then it could be exit dose from opposite field, especially if using say 15 MV photon, that itself could be close to 70 or 80%. Sometimes you have forgotten. Then increasing field size, more scatter, then oblique incidence, because oblique incidence also increases. So sometimes in treatment of limbs or in chest wall, there's oblique incidence and the skin dose is more. And then scattering from the shielding or the material. So in a single or multiple photon fields, as I've mentioned, I will not go into the details, just briefly talk about single photon fields. Mostly in palliative setting, sometimes in curative setting, and everywhere else we use multiple fields. And I'm repeating it again because it is so important. Patient positioning has to be optimal, and it is to be optimal for the beam entry and exit. It should not, organ should not come in the field. And that you see that the planning imaging, whichever imaging you use, either CT based or X-ray based, it should include the entry and exit of the intended beams and CTVs, and use contrast only if it is going to help. Okay, this again I'm repeating because it's very important. Just few points. You know your physics. If you don't know your basic physics, you will not be able to come up with a good plan. Use be careful always. I'm repeating it to sort of the extent of boring. Do that. See that patient doesn't get skin reaction. Choose the optimal energy. Use the best possible beam for that patient. And the crux is use the beam direction, orientation of the beam, which is ideal. It may be routine in the department, but you have to understand why it is being there. And through that, you use your physics, logic, and anatomy, and you modulate the beam and shape them as required. Now, what are the steps? Now coming to specific steps. The beam, not after you have chosen your direction, when sometimes how you decide your direction, that it traverses the shortest path within the body. That is number one. Second is it irradiates least amount of normal tissue before it reaches the target volume and after it has crossed the target volume, because it is still going on. The beam is going on. So that is always. And sometimes you are something which is the shortest path is not achieving the other thing. And when we talk of normal tissues also are ranked. Some normal tissues are more critical than other normal tissues. So that's what critical organs. So you have to avoid a critical organ like spinal cord, kidney, heart, etc. Then you avoid organs at risk which have very low dose threshold, which are such as a lens. Then you have to avoid parts of unusual anatomy. Suddenly somewhere the contour changes very much, or its skin fold comes, or sort of bump comes, that area. So sometimes these are the areas which will perturb the dose distribution. That is one thing. Now, when we're talking about, that is for one beam you choose, like that when you are using multiple beams, the intersection area of multiple beams is as small as possible. That is one thing. And it should be as much closer or conform to the shape of the planning target volume as possible. And when you're doing two fields, it is not possible. The intersection of two beams is generally much beyond the planning target volume. In the anterior posterior field, it will be much beyond the planning target volume anteriorly and posteriorly. So sometimes you may use more beams, like third or fourth beam. So if the intersection area of two beams is much more than the PTV, then you add the third field or the fourth field, and you start, of course, shape the fields also. So I'm just showing some examples. Now we will come to the real crux of planning. So if you look at here, this is a bone. It's in the bone. Okay. So let us say it is a tumor affecting the bone. It's a metastasis or something else, and this is your GTV, and then you're given margins to that because there may be infiltration of that, and you could treat with different ways. So one way of treating it would be like you're treating on phase. Okay, with electrons if you use, because it is bone, the dosimetry uncertain. If you use photons directly over here, then the photons will exit through this. That will give unnecessary radiation. If you use only direct anterior field, it will exit so much this side. If you use this oblique will cover through that, but the posterior part of the target volume it will underdose because the thickness from here to here maybe is 7 or 8 centimeter. So you might use two tangential fields. Okay, this is just one way of just giving an example. Okay, so that will spare the maximum amount of the brain, and you will achieve a relatively homogeneous distribution. So, it looks a little odd. Of course, this was a palliative treatment. The patient is not expected to live, and very short expectancy. It's a fungating wound for some other, say, skin cancer. You might just even give a single and lateral field where just a palliative treatment. But if a patient is expected to live beyond few months, then you should plan better. Now I'm showing this example in the brain. Let us say a frontal tumor, right? Frontal tumor. So the gross tumor volume and your target volume. This is something in the center. So when you are treating this beam, there could be one anterior beam okay, shortest path. Then the other shortest path beam would be from this side, from the right lateral. From the left lateral, if you put, it will have to traverse much more. So this is not the shortest path. So two beams, and when you're the intersection of the two beams will be this area that will have the least. So that will really almost conform to the target volume. But if whatever reason you want to reduce it further, then you may have to have a third beam or the fourth beam. So the more beams you add, there is less and less usefulness it becomes. So this is something. Now, this was in the center of this, if in the target volume. So one beam you put from the anterior because it crosses the shortest beam, but it is also exiting. You have to look at. So before entering the target volume, it has irradiated very little of the normal tissue. But after it has exited from there, and if you remember 6 MB photons, even at 15 centimeter, more than 50% of that is remaining, the dose, it has given this dose. So one anterior beam, the exit dose, you are not happy with this. And plus the coverage also says, suppose this is at 2 centimeter from the surface and this is at 7 centimeter, this area is not getting full dose. So you're not happy with the anterior beam alone. Then you will add, but because this is in the center, just adding from one beam will not help. So you will use one anterior and two laterals. And then of course, after doing that, you will shape the beam. So the principles that you use it from the shortest path, from the closest from the tumor. So it is anterior. And then because it is the exit dose, you're not really happy with it. You have to add the second beam, and this because in the center, you are adding two beams from the side. And then we will talk about later how we will modulate these beams and what will be the dose distribution. This is just to put your beams. That is the first thing. Okay, here I am not talking about the patient positioning and all. That is very individualized that you have to decide. So when you see a plan, how the beams are arranged, I'm talking of IMRT plan or a VMAT plan. Whenever you see a 3D CRT plan, you will typically see that this is the principle on which the beam arrangement is decided. And I think in the entire treatment planning process, the beam arrangement or the gantry angle is the most important. Then, I mean, obviously, it's very, straightforward. You will shape the beam according to your target volume. Whatever is outside the target volume, you will, if you can shield it, you will shield it. Okay? Then you will modulate the beam, so the dose distribution is important. But if your beam orientation is wrong, the problem that it creates, it's not easy to take care of those problems because of wrong beam orientation. And this is something which we don't discuss. It is for you to, as trainees, to see and understand that you have understood in this location, in this body part, in this tumor location within the skull or within the abdomen or within the thorax. This is the beam arrangement for 3D CRT or 2D RT beams. Again, this is in the center. So this. So now I have shown this. So the previous one was, if you look at it, this was compared. Remember this one, this target volume. Now this target volume. Here, if you put it from anterior, so if you go by the same principle, one beam is from the anterior, it is exiting all through that. You will say, okay, I'll put one anterior and two laterals. Okay. So again, you see the laterals also are, sparing very little because there's very little normal tissue. So in this case, if it was especially in a palliative setting, you could have simply used parallel opposed field. So one beam from the right lateral, other beam from the left lateral, and there is very little normal tissue that was irradiated. But this is only in the center. When you go higher and lower, superior and inferior, you might find that there was scope of sparing the normal tissues superiorly and inferiorly, which you could have done even in parallel opposed field also could be shaped, or you could have then used an anterior field also in this case. So you have to be, so in this case, you will not automatically use three fields. You have to see whether the addition of a third anterior field would really help. And depending on the clinical context and what you can save and what you cannot save, maybe in parallel opposed field that you would have the skull or the scalp dose will be much higher because it is through and through, especially if you're treating on cobalt. The patient would have more long-term alopecia. Whereas if you're using three field, the dose to this scalp would be reduced, not for the brain, and patient would have better hair regrowth. Now this is located posteriorly, so this could the solution, the beam could be one posterior and one lateral. But again, you see the amount of is there that you will not get a proper coverage. So if you want a very homogeneous coverage, you may have to use a third field, or you may have to use an oblique field, different kind of field. So this is a little odd. You have, again, the principles are same, how you would appear, your field direction. So now I will bring in the percentage depth dose. We had showed the percentage depth dose charts. Now, sometimes when you look at charts, just the table or the curves, you are not able to in our time, and even now some students do it. They use percentage depth dose charts, they overlay, and then they draw the resultant dose distribution. But I'm just giving you a simple way, okay? Is you just draw, and I've drawn it at equidistant. This is the anterior field. Okay, this is like the box, look like a boxy box shaped target. This is a target volume, 100%, 90%, 80%, 70%, 60%. This is for visualization and for concept. Really speaking, as the lower ISO doses, the distance between say 70% and 60% will be more as compared to distance between 90% and 80%. So in this, so suppose. So this was 90% and this was 80%. So this box, imagine these are voxels. Okay, in this tumor, this gets 95%, this gets 85%, 75%, 80%. Okay. So if suppose it was a palliative treatment and you had this was at say 5 centimeter depth, you are getting 85% with a single field. You know that in this setting, and most of it is getting around 90%, you are acceptable, that is acceptable to you. So you accept a single, I'm sure, an anterior, it could be a single anterior or posterior. So, but if it is a curative setting, then you see that 95% of the prescribed dose is getting. So that's why in curative setting, very seldom you would use a single anterior photon, or single anterior or single lateral photon field, except maybe it's at only few centimeter depth, like some orbit or something else. There are very few selective situations where you would use a single photon field for a curative setting. Because the other issue is that there will be exit of that, because it is exiting through and through. Okay, so you would use it only if the coverage by 95 or 85% is acceptable. 85 would be in palliative setting, 95 is that, and the homogeneity is there, and the dose beyond PTV is acceptable, or it is the best trade-off. So mostly the dose beyond the PTV would not be acceptable. You would not be happy that all this area gets 60 or 50%. So that's why you would not use single anterior field. That is the reason. Otherwise, for so many things, you can just use a single anterior field. Now comes when you have one. So now in this, the target volume is this is this this is a square shaped body that is assumed, and this is the target volume. So one is the single anterior field, 100, 90, 80, 70, 60%. So, and then you have added, so because by the time it reaches, so you have added a posterior field. So posterior field, it is again 90, 100, 80, 70, 60. So in this situation, what has happened? So if you look at it, this area, this voxel, it is getting 95 from the anterior field and 65 from the posterior fields. 95 I've kept because 95 is the average of 190. So this gets 160. I'm not made it a percentage also. Just look at the numbers, total numbers. So it gets 160. Every box in this or every thing in this area would get one same dose. So you get a homogeneous dose. But mind you, I have gone only up to 60%, the depth is not. Suppose you are using cobalt 60, where the percentage depth dose is less, and this separation, anterior-posterior separation is 25, then it will not happen like this. Then there will be some areas that you will start getting high dose and some areas. So I will talk about that solution. So homogeneous dose distribution if interfield separation or IFS is not too high for the given photon energy. So in that situation, you could use parallel approach. The other thing I wanted to say here is you can see the normal tissue in exit and entry before it enters. This is very little and it is such a subcutaneous tissue, so you don't bother. So in many situations, you would use parallel approach field. Like you have to sometimes bilateral neck, it's a parallel approach field. But there is a caveat: you could get a hotspot anteriorly and posteriorly if the interfield separation is more, and the hotspot could be as high as 120%, 125%. Like I gave an example of using a telecobalt with an interfield separation of say 25 centimeter. You can get a really hotspot. It would result in subcutaneous fibrosis, etc. Plus, there is a constriction of higher isodoses, especially the 95% isodoses in the center. So there are consequences and solutions and trade-offs. So this I mentioned, the consequences of hotspot anteriorly and posteriorly is the fibrosis, and sometimes this hotspot is large and comes on the rectum. It could also be the posterior hotspot in pelvis. And the constriction, the consequences of this is, first of all, it's a constriction, because we use the term sometimes hourglass. It is not like a typical hourglass when it in the center it just becomes. It is not that typical hourglass. It is a slight constriction. The constriction could be just few centimeters. And I'll have a slide. I will show that. Okay. So the solution. So hotspot anteriorly is basically 1 to 3 centimeter slab. And in cobalt, if it's a low energy and the separation is more, and 6 MB when the separation is really beyond 22, 24 centimeter. So how you take care of it? Either you increase the energy or you add more field so that you don't get it. And for the constriction of 95% isodose, which could be sometimes with low energy and high separation, it could be up to 3 or 4 centimeter inside. So one is the solution depends upon increase the energy, increase the width of the field, or you use a 4 field or a 3 field box. So when you use that you will take care of the constriction. Otherwise, you end up, increasing the width of the field looks like very simple. You just increase the width of the field, but you're also irradiating more of normal tissue. So some of the X-rays pictures, if you see that this is 95%. So this is 6 MB AP field. There's a slight constriction of the 6 MB photon, not too much. Okay. So depending upon, like you say, anterior hotspot, 110 centimeter, 110%. And as you increase the energy, this is a low energy and the other is a high energy, you don't get rid of the hotspot. Okay. So this is a 4-field box. A 4-field box, what you see is typical peculiar thing is you are getting this 110% anteriorly. Okay. So there are 2 reasons for this, that anteriorly there's a missing tissue also here. Of course, you don't put 4-field box where the whole body is covered, without any sparing. So there is missing tissue here. Plus, you look at the point of prescription, it is not in the center of it. So you have more dose from there. So that's why you're getting little hotspot. So this is, of course, it's written unapproved. This is just for practice. The residents made it. So this is just to show. Okay. Now what I'll show you is the more complex for you to understand how when it is not parallel opposed. In parallel opposed fields, the dose was high or low only because the separation was large or the energy was less. Now, moment it is not parallel opposed field, the fields are at a direction which is not 180 degree. Then new things come into picture, and I will show you why. So imagine there is the target volume which is lateralized. Okay, which is lateralized, and if you're using an anterior field only, it will underdose this area. And if you are using parallel opposed fields, all this area which will get unnecessarily dosed. So you're using anterior and right lateral. So imagine the principle, the shortest distance. But what will happen when they're using anterior and lateral field? And here, for just to explain that there is no missing tissue, because you will get fixated that is a missing tissue. There is no missing tissue. It's a absolutely rectangle. Okay, so there's no missing tissue. Of course, human bodies would have some missing tissue, but then also this is the purpose why wedge is used. So there's no missing tissue, but anterior and right lateral field. So in the anterior field, the dose comes down from 100%, 90, 80, 70, 60. And the right lateral field, again, the dose, the percentage depth dose, it gets attenuated from 100 to 90 to 80 to 70 to 60. So what happens is, can you all predict, okay, those who did not hear the previous lecture, and from just tell in this, where will be the hot H and where will be the cold or lower dose? And what are the cons? First of all, you should now get it right on your own without any prompt. Maybe at least after this lecture, because when you're asked, still people struggle, where will be the hot area, where will be the cold area. And once you don't understand that, you will never be able to come with the solution intuitively. Once you know that, your solution will come to you intuitively. So how to show that? If again, I have just shown that, so in this area, this box, which is here, it is getting 95% from the anterior field, 95% from the lateral field. So it gets 190. And the just diagonally opposite to that, which is this area, it is getting from the right lateral field also, it is getting right lateral field, it is getting only 65%. And for the anterior field also, it is getting only 65%. So it is getting 130. Okay. So look at this gradient. So this area, as a result, this area will get higher dose, let us say in the center, whatever is the prescription point, the center where it is getting everything is getting, say, 160 and this thing. And this area would get a lower dose, which is the cold region. So just the area, if you put it in the other words, the part of the body, and it doesn't care whether it's a target volume is there or not, any part of the body which is closest to the two beams. So this part of the body is closest to the right lateral beam also, anterior beam also, will get the highest dose, hotspot, because the beams are, and any part of the body, whether it has tumor or normal tissue, doesn't matter really, which is farthest away from both the beams will get the lowest dose, which is the cold. So how do you take care of that? Because this was getting hot. So this is the anterior beam. So in the anterior beam, you had to reduce the dose, which is on this side. So you put a wedge. Wedge is basically, it is a physical wedge, but you could have a dynamic wedge or other wedge. That's the concept is same. So what happens, the wedge, I have not kept separate slides for wedges. It will reduce the intensity, because if you remember the attenuation, when it goes through a material, so there's more of the material there. So it will, there will be more attenuation. That's why I mentioned attenuation of the beam on on the right side of the anterior beam, there will be more of attenuation. And in the same way, in the right lateral field also, you put a wedge. And in this, the anterior part of the right lateral field have more of attenuation. That's how you decide the direction of the wedge. And after you do that, you will get a, okay. What will happen after you do that? This hotspot will be taken care of. So you will not get a hotspot will be relieved. And what will be the wedge angle and all, I will come later. Okay, this is just to understand wedges are required and the orientation of the wedge. Sometimes the wedge angle will be different from what you calculate because of missing tissue and all, but this is the primary thing. Okay. Now coming to, so you had one anterior field, one right lateral field. Then this target volume, I've moved it in the center. Previous one was close to the, if you remember, it was close to the right side. This is in the center. So then it would say, okay, let us use 3 field. When you're using 3 field, now imagine if you can write where would be the hot spot and where will be the cold spot. Okay, you have to think, and I've again put a box. You take a minute, just put where will be the hot area, where will be the cold area. And if you get this also right, then I think, you have understood a lot of basic physics, how beam interacts and the attenuation process and how to combine percentage vectors. Okay. Just think where would be the hot area and where would be the cold area. And when I will show the numbers, it will be immediately, that's where it will be, but you have to get it right now. Okay, I'll show it. So you look at it, this part, anterior part, it is getting from both the right lateral and left lateral. Okay, it is getting same amount. You see, two things will be same: 95, 95, 65, 85, 95, 75. So as the voxel you combine, you look at it in the lowest part, this area, everything is getting 225. Here everything is getting 255, and in the center, this is the center between 235 and 245. Okay, so here the dose, how the doses are combined, you will have the cold area posteriorly and hot area anteriorly. So now you have understood. Now once you have understood, predicted where will be the underdosed area, where will be the overdosed area, you know the solution. Now you know what you have. One thing in your hand is a wedge. Whichever is the thick end of the wedge, the dose will be reduced more. Okay, so would you put a wedge in the anterior field, because wedge has to have a direction. Okay, so we are only looking at one axis. Of course, we are not looking at coronal axis and sagittal axis. So would our anterior wedge help? No. So what wedges would help in the two lateral fields, and whichever side is hot, the thick end of the wedge has to be that side. Whichever side is cold, the thin end of the wedge has to be that side. And again, I am showing like a box. without any missing tissue so that you don't get confused by missing tissue. So you put two wedges, one thick and anteriorly, that is will take care of this. Okay. Now I am showing a this is a 4-field box. Okay. In a 4-field box, now who would predict? You just write down. So 4-field box, imagine this is all going from 100% to 60%, from posterior field is 100% to 60%, right left lateral field again 100 to 60, etc. So where will be the hotspot? So this is where you would use a 4-field box, like a cervix where there's a lot of tissue on both sides to be spared and tissue anteriorly and posteriorly to be spared. That is where you will use a 4-field box. So where will be the, and again, no missing tissue. Okay. So where will be the hot area? Where will be the cold area? If you cannot get it right, I will show you. It will be a homogeneous dose, like in a parallel opposed field, because everything, the right, just imagine these are two set of parallel opposed fields. So right lateral and left lateral is one pair of parallel opposed field, and anterior plus posterior is the other set of parallel opposed field. So basically you're using two pair of parallel opposed field and the distribution is homogeneous, and you don't require any wedges. Now I will introduce this, okay? Because sometimes, because anteriorly there is a missing tissue, because in the thigh region, suppose if this was a missing tissue here and this, because of the missing tissue, this area gets high dose. You might use a thin wedge, say 15 degree or 20 degree wedge. Of course, in dynamic wedge, you don't have to use a specific degree only. You might use a wedge, but that is with more advanced planning when you're doing 3D CRT planning with a, proper on each slice you have contour. But primarily, it does not require a wedge. That is the standard answer. Sometimes for missing tissue, you might introduce a wedge like a missing tissue compensator. That is something. Okay. If you are not doing IMRT and something else, then if it is required, that is all. So the other use of wedges, I think I will cover this only, is please remember wedges are primarily, they were designed to be used for when the beams were not parallel opposed. Either they were anterolateral or oblique or whatever, because some parts of the area which were closest to both the beams were getting high area, those parts of the body which were farthest away from both the beams getting low dose. They were the primary purpose of designing and using wedges, but we know that wedges can also be used as missing tissue compensators. That is secondary use in very few selected sites. Like suppose you're only treating vocal cords, small field, where the missing tissue is happening only in one direction, and anterior, neck is narrow and posterior it is broader, and there you may use wedge to compensate for that. But the moment it's a more, if you are treating say from zygomatic arch to supraclavicular fossa, then you can't use a wedge because it will do the uniform attenuation across the beam. Then you use a tissue compensator, which takes into account the 3-dimensional this thing. This is doing it only taking into account 2 dimensions. Okay. So in small vocal cord fields or in breast fields where there's a missing tissue, so there are very few selected areas where you use wedges for as a missing tissue compensator. Otherwise, wedges are only and only for when the beams are not parallel opposed, and because they are not parallel opposed, parts of the intersection area gets high dose and gets low dose. Okay. So this is again, I'm sort of now I'm showing the angles. Okay, what are the angles that we will see? Okay, so the angle of the wedge would be, I've shown it will be 45-degree angle. So first you understand the orientation, the need for wedge and orientation of wedge. Now the angle, because otherwise you just learn what is a wedge angle, what is a hinge angle, wedge angle, etc., without doing anything else. So I'm deliberately introduced it much later. And again, no missing tissue. Okay. So thick end facing each other, thin end away from each other, because you want greater attenuation by thick end of both wedges and lesser attenuation. And the wedge angle is equal to 90 minus hinge angle by 2. Okay. So 90 minus 90 by 2, here it will become 45 degrees. Actually, any formula you can test by seeing how it functions is Just give me a minute. Okay, so where were we? How do you test your formula? There's something in parallel opposed field you don't use wedge. That means don't use wedge means wedge angle should be 0. If this formula is correct, what will be the wedge angle in parallel opposed field? That is how I ask students. And when they get the answer right, they say, wow. So 90 minus what is the hinge angle in parallel opposed is 180. So 180 by 2 is 90. So 90 minus 90 is 0. So this formula is correct because in parallel opposed field, you don't need wedges. Okay. Sometimes in parallel opposed fields, like in vocal cord or breast, use wedges only for missing tissue. Otherwise, you don't need wedges. Here you need this wedges. Now you have 2 obliques. Okay, so that was, just imagine you were treating, one way of treating vocal cord, let us say, is with 2 oblique, anterior oblique or right and left anterior oblique. In many other cases in the body, we use anterior oblique. It could be like vagina or some other portal. It could be same thing, could be for posterior oblique. So what all I have done is the anterolateral thing, it has just been twisted. So you get hot spot anteriorly and cold spot airly. Okay, so these are open field. With open field, this is what will happen. And what solution? Again, the same thing. All you have done is just sort of change the angle. So here previously we were calling it right lateral field, we are calling it right anterior oblique, and this anterior field has become left anterior oblique. And you have used 45 degrees because the hinge angle is again 90 degree. So in two obliques, if the hinge angle is 90 degree, you still require wedges. The wedge angle will be 45 degree, and the orientation of wedge is always the thick and together. That means wherever the area you get hot spot. So first and foremost, you have to understand which area will get hot, which area will get cold. And once you know that, you know where will be your thick end and where will be your thin end of the wedge. Again, the wedge pair, it is the same. Okay. So now for different orientation of wedge, so if you looked at it, so whatever orientation of wedge, you can calculate the hinge angle. Okay. Okay. So some examples, like 2 field versus 4 field. So in 2 field, you saw that the anterior posterior field, you get this area gets hot, 114% is the D max. Okay, and it is planned, and this is what you want to treat. You're treating much more, and this is with 1.2 MeV. That means the cobalt this thing, and you're giving this 95% isodose is isodose washing. You can see slight central constriction. It is not like a hourglass, but slight central constriction. And if you use a 4-field box, then ignore that target volume that is drawn. That is, you've just sort of put the fields for showing. Then you get a very good homogeneous distribution because the 4-field, as we showed in the earlier this thing. Okay, so when we're using a 4-field box, so what is the trade-off? Okay, so trade-off is that, you said, okay, well, this is perfect. What would be the trade-off? Why would anyone use a IMRT? Okay, one is, of course, it is not conforming too much. Then this lateral here, we have only showing 95% isodose, but the hip joint dose, otherwise in anterior posterior field, the hip or the femoral heads were hardly receiving any dose, or the femur parts of femur were not receiving any dose. Now suddenly you start getting dose, and if the lateral separation was quite large. Here the lateral separation, we have considered everything together, but the lateral separation was say 38 centimeter, and you did not had more than 6 MB photon, you had only cobalt 60, then that dose could have been quite significant. Okay, so you look at the hotspot. So this is Three field planning, one posterior and two lateral, and you did not have, this is on a cobalt, it's a large separation, it's a huge patient, okay, and very large, you can see from the amount of abdominal fat, huge patient, you used only cobalt, one posterior field and two lateral field, let us say it's a case of rectum, then what you see that the dose is much higher in this region, because that's what we were describing, that don't just look at the dose at the depth where you want to prescribe, but how much, if the prescription dose is much less, percentage depth dose is much less, the entry and exit dose will be much higher and you will get a hotspot. Okay. So this is one thing. And whereas if you have used a 6 MV photons, then because the 6 MV photons has a higher percentage depth dose, it is there. And here we have not used wedges. Because we have not used wedges, if you remember the three field plan, anteriorly more and anterolateral, this side, this part, this corner is getting high dose. Okay, if you used wedge pairs, so the high dose here is because of the field arrangement, and plus there is more of missing tissue here. That's a combination of that. So it is getting 126%. Okay, so same way with different field arrangements, you show on a cobalt 3 field versus 4 field. If with 3 field, even with wedges, this area was getting, and just look at this point. This area you're getting a hotspot at 138%. So one would wonder why you are getting at this particular. So you've tried to compensate here, but towards the thin end of the wedge, there is increased transmission, relative transmission. So you may have a hotspot under the thin end of the wedge. So now I'm showing one case where actually how you will do the planning. So suppose this is the same, we're talking about the right frontal tumor. Let us assume it's a glioma. It's a low-grade glioma. You've given small margins and you're doing a 3D CRT. Okay, you have done a CT, but you're not using IMRT. So this is a central axis. Then because the tumor is not square, where it's shown. So at superiorly, say 1 centimeter short of the superior end of the tumor, this is how it looks, and this is 1 centimeter. So the shape of the tumor varies, superiorly to inferiorly. So what will be the beam arrangement, and whether it will be SSD or SAD? That is one question. So the beam arrangement, if you look at what we've said, beam arrangement should always have the shortest distance. That is number one. Then you have to everything. Ideally, all the conditions should be met, but it is never possible. So you see that maximum conditions are met, and which one has the least, penalty in terms of this thing. So shortest distance would be from. If you say from anterior, yes, but then it is exiting from here. So you have put a lateral field. So if you're using anterior and lateral field and look at the sloping surface, so the best method would be isocentric, or SAD is also isocentric. So you get the isocenter in the, on the tumor. So this is right lateral field, anterior field, and this is your isocenter. So it becomes an isocentric technique. Okay. So initially I'm just showing only 2 fields right now, just one anterior field and one lateral field, and the field border that you have chosen. So all the physics that you have learned so far is applied here. So when you're doing a planning, see, the purpose of knowing the beam characteristic and all that is not just for fun or memorizing. Okay, it is to apply it. So if you see your target volume, and this is, let us assume this one is the PTV, your field border is away from that. Because why it is away from that? CTV to PTV you take for setup uncertainty, all this movement and all. This is because there is a penumbra. There is a penumbra, so you take into account that. And as you see that you have to cover where the maximum dimension of the tumor, the fields you have designed, the rectangle or square you have designed, where is the maximum dimension of the tumor? Because on the machine, the beam you will get is either rectangular or square. That is all you can get. So that you design your field, you open your field like that. And because this is anterior and lateral, then what will happen, as we have said, where will be the hotspot and cold regions, as we know that one beam from anterior, one from lateral. So all that you have learned is that this area will get hot. This is how it will look in the, so now sometimes you're used to looking at in the transverse section, but the moment it comes to looking and sagittal plane or coronal plane, sometimes you try hard to understand. Again, the simple way to remember is see which will be closest to both the beams. Okay, here you know that this will be there. Here it will be more anteriorly. Here it will be more laterally on the right lateral side because this beam is coming from this side. So this is your hot area, and this will be the cold area, the opposite of that. And here the cold areas. So you have to imagine in all the dimensions. Like film directors, they use photography. Even in black and white era, they use photography. It was all about shadows. They would imagine, this camera angle there, this is how it will look. So you also have to imagine where will be the hot area, where will be the cold area. And once you get that right, you will start getting it intuitively. Everything else would really follow. Okay. So once you have understood this is the cold area, hot area, I know the solution. I put one wedge in the anterior field, and that wedge direction, and you know that because whichever side is from the other field is coming, it has to be that side because that area will be hot. And another wedge in the other field, which is right lateral, in this direction again, and based on that hinge angle, wedge angle is equal to hinge, 90 minus hinge angle by 2, it will come out to 45 degree. In addition, there's a more of missing tissue here, but not so much. So you might see that, okay, maybe instead of 45 degree, it might require 50 degree or something else. But broadly remember in that formula. Okay. And this is what you see actually in one of the plan that was made by one of our residents. So in the anterolateral field, open field, this area gets hot, this area gets underdosed. And once you put wedges, this you see homogeneous coverage of that. So this is what, and again, you see towards the thin end, there is higher transmission. So be aware. If suppose there was a spinal cord or something else, then be aware. Otherwise, it doesn't really matter. Small area gets high. So now so that was just simple field. Okay. It was, now that we were looking at only at the central axis and in the central axis at that plane. But as I showed, the tumor is different shape and size superiorly, inferiorly. So here, actually, very little of the area was getting, the shape of the isodose, let us say 95% isodose, would have covered more or less the shape of the target volume. Okay, more or less the target volume. As we will see that, so 95% isodose is covering more or less of this thing. And to reduce this, you could have reduced the field width and would have covered. But you look at it superiorly and inferiorly, it is treating much larger area, which is then it is required. So unnecessary radiation. Plus, now I have drawn the target, another critical structure. So there's a pituitary hypothalamic axis, optic chiasm, and all those things. So how to take, and then you're not doing IMRT. Okay, when in IMRT, you just draw your structure and then, some physicists will do something. So IMRT is also evolved using these principles, and then we know how much to modulate and how to modulate. The other thing you see that the beams here I've shown, I've just drawn them to be divergent beams. Okay, that is how you get. So anteriorly it was this much, then it is diverging, and all the beams are diverging. So you not only you want to spare all this rest of the normal tissue, you want to reduce the dose. Now, in particular, you want to reduce the dose to pituitary hypothalamic axis and the optic chiasm. Imagine, suppose he's a 12-year-old boy. Okay. Pre-puber this thing. So then, it will not only cause imbalance of hormonal axis and, other factors. So what you can do is, first of all, field arrangement, you have decided already. Then you could put in the lateral field, because all this you could shield there. Okay, you could shield there. And if it is simple, you are using 2D simple shield, and you don't have, but if you're using conformal shield, you could be more. Let us say it's a simple shield. You shield this corner. Anteriorly, I have not shielded here. Look at this point. I have not put a shield because, you have to give a margin. See, the fields are away from the, you keep a distance of about a centimeter or so from your PTV, the field border. Field border, first of all, you should know what the field border is defined by. It is not 95%. It is defined by a certain isodose, 50% or whatever. You should know your beam. And if I put a shield here and keeping a margin, I'll be just shielding a thin sliver of maybe 6-7 mm of scalp. It will not really achieve, because as such, the shielding effect is lost after some depth. So I'm not putting a shield here. And again, putting a shield here, it is very tempting to put a shield here. But again, any shield which is very tiny is generally not relevant. Okay, so that you have to see. You might put it, but it won't help. In the anterior field, I have scope. Now in the anterior field, I have a scope to shield, put all the four corners. But if you see that this critical structure, I am able to shield from the lateral field completely. This is outside the field. But from the anterior field, only part of this I'm able to shield, rest I'm not getting covered. So it is getting, basically this critical structure is getting dose, half the dose is from the anterior field. So it is getting little less than half, because the dose is prescribed, at this point isocenter. So it's getting little less than half of the dose of the total prescribed dose. So how do I take care of that? If I use a third field, then basically I'm able to shield this critical structure from two laterals. So then it will get only 1/3 of the dose from the anterior field, and that will be taken care of. Okay, I think I will just, yeah. So now coming to an end of this lecture. So we talked in our art series that we have to know the anatomy of the human body, because that is the canvas on which all these genes, all these beams are going, they're interacting with tissues. And the human body is not a box. For explaining, I was deliberately using a box shaped, body, because people get too fixated by missing tissue. But in reality, the body shape is different. Each person's body shape is different. Internal shape is different. External shape is different. So you have to know all those things. Plus, inside, if you look at the surface and the shape, the planes and relationship, the physiology, reserve and tolerance, the bone and the calcium and the metal, all these things come up. The air and the water and the density, the motion, rhythm and changes, and many things we don't even see. So what distribution is produced for the calibration of the machine, and on the TPS data is beam data is put by using phantoms. These are fancy phantoms, they're very expensive. But the human body is very different. So after you have understood your basic aspects, then all these aspects you have to understand and take care of in your planning. Okay, but you can do this only if you have understood the previous parts of simple and basic 2D and 3D planning. If you have not understood, then it is impossible to reach to this level where you're talking about more fancy planning. And not only that, in tumors, so in terms of radiobiology, you have to know. So when we talk of treatment planning, that which part of the tumor is not homogeneous. It has stroma, it has tumor cells. Tumor cells are part of a tumor is necrosed tumor, part of it is hypoxic and radioresistant tumors, and part of the tumor is growing tumor. So by the time you will be into full practice, I'm sure a lot of biologically adapted radiotherapy would be in use. Today we use FDG PET, but there are many more isotopes or things will be used which will tell you about hypoxia imaging and other molecular imaging. So this is the final slide of today's. At the end, you have to write a radiotherapy prescription, patient ID, position and setup instruction. That is very important. And finally, when you see setup, many of you see setup, are you getting reproducible setup? Sometimes because the initial positioning was such, you have not paid attention to that, it is impossible to get a reproducible, or you have not recorded and given proper setup instruction. Site has to be mentioned, total dose per fraction, number of fractions per day or per week, type of radiation, number of fields and techniques, and very important, I have not talked about special techniques, but the technique has to be clearly spelled out and everyone should know what is the prescription point. And why I'm mentioning this is at least even if it is not mentioned, when you look at a plan, you should know where the plan is normalized, what is the prescription point. And more often than not, you would find that even in a parallel opposed field, the prescription point is not at the mid plane, but at somewhere else. And if it is not, if it is an open field and a mid and parallel pose, it should be mid plane. If you're doing anything else, then you're doing differential weightage. And the moment you start doing differential weightage, whatever I showed you in your basic concept, that will not follow. So you be aware of that. Then after that, what are the special instruction or thing like you use a bolus, and sometimes you require a patient specific QA. We have not basically covered that aspect because this was all 2D and basic 3D planning, but that is required. So in today's whole thing, I will Okay, so the bottom line is that considering the aspects of physics, that if you don't understand physics, how X-rays interact with matter, low energy X-rays, high energy X-rays, with different type of matter, there is no way you will understand why you get a particular type of percentage depth with cobalt 60 or 6 MV or 10 MV. Without understanding scatter and absorption, you will not understand how attenuation is happening, how you can modulate the beam, what happens when the beam is modulated, because there is scatter also, how the shielding effect is lost. And depending on the orientation, because percentage depth dose, when you combine different percentage depth dose, what happens, which areas get hot, which areas get cold, and how do you take care of that? So I think once you understand that, it will really help you to understand. And imagine this, one of the slide I showed, principles that you use, decide one beam or more than one beam, the direction from which the beam is coming, the shortest distance, then look at the exit dose also. When you use more than one beam, what happens when you use more than one beam? So all those things, I will share the slide and you look at this. And I think someone has asked, King, I don't know who's King, has asked, thank you so much, sir, for such a good lecture. How to correlate 3D planning to 2D marking? Which isodose level to correlate? Okay, so see, 3D planning, normal, simple 3D planning, you do that, you know that for this 3D planning, basically, you know the borders. On the skin marking, you only see the field borders. So the superior, inferior, medial, lateral. Okay. In the anterior field, it will be, or posterior field, it will be superior, inferior, medial, lateral. In the lateral fields, it will be, these borders. So on skin markings, you see. So if it is very straightforward, just anterior, posterior field, so you how to correlate 3D planning to 2D marking. Like let us say esophagus. Esophagus, if you have one anterior and two posterior obliques, okay, in a 3D planning, you can only see the marking of the anterior portion. Okay, you see whether it is expected the superior and inferior border is correct. But the two obliques, skin markings will not be able to see. But if you are sure that that is isocentric, if your isocenter is accurately placed where it should be placed, and you have reconstructed images, you will know, or a 2D simulator X-ray, you will know that will come at the same place. So this is how it is done. And I will share the PPT for quick revision. Someone wants to do quick revision today. Okay, I'll share the PPT quickly. Thank you very much. I think we didn't expect it lasted so long. I'm glad I, in between thing I removed. Anyone else you want to say something? No. Okay. Please post the link to Telegram group. Yes, I will. Thank you. On a Sunday evening, so many of you. Okay, bye. We'll stop that.